Section 15 of the Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lawrence Trask, Mount Vernon, Ohio, interfaceaudio.com. The Science History of the Universe, Volume 4. Edited by Francis Rolt-Wheeler. Chemistry. Chapter 11. Berzelius and the Development of the Atomic Theory. Complete success had rewarded the exertions of Lavoisier, and through the efforts of Proust, Richter, Dalton, Gay-Lussac, and Davy, the spirit of order was creeping in on all sides. But it was exceedingly fortunate for chemistry that an investigator with the sense of coordination that Berzelius possessed should have made his advent just at this time, when laws required confirmation and theories nourishment. The foundations of the new system required extension and generalization, and how opportune was the appearance of one who could illumine the whole domain of chemistry. Berzelius ruled as an autocrat for over a quarter of a century, and the modern chemist can hardly over-extol his obligation to him. Johannes Jacob Berzelius was born at Walversunda in Östergötland, Sweden, on August 20th, 1779. His father was a schoolmaster in Linköping, and died 4 years after the birth of his son, who for some time afterward had to endure many privations. Berzelius studied medicine at Uppsala and subsequently practiced, but he had early acquired a devotion to chemistry and kept in close touch with it. He was but 20 when he undertook his first extensive chemical research, an investigation of the medical springs at Medevi, in the neighborhood of his birthplace. A short time after, in 1802, in conjunction with Hisinger, he commenced the examination of the action of the electric current on various salts, with the most far-reaching results for chemistry and for himself. For almost immediately, the desire to keep so promising a student in Stockholm induced the authorities to create for him a new academic position, that of assistant professor of medicine, botany, and pharmacy at the University of Stockholm. In 1807, he was installed in the chair of medicine and pharmacy, and also taught chemistry at the military college from the year 1806. In 1815, he accepted the chair of chemistry in the Chirurgico-Medical Institute of Stockholm, where he accomplished the researches which made him famous, and where his lectures enabled him to impress his views upon the rising generation of chemists. Among his pupils may be mentioned Heinrich and Gustav Rose, Mitscherlich, Wöhler, Christian Gottlob Gmelin, Magnus, Mosander, Svanberg, and Sefstrom. From the year 1818, when he was nominated permanent secretary to the Stockholm Academy, of which he had been a member since 1808, and more particularly after 1832, when Mosander succeeded him in his chair, Berzelius devoted himself to literary work with a subservience which has hardly been equaled from a utilitarian standpoint by any chemist before or after him. He died on the 7th of August, 1848. Berzelius was an exceptional observer and a most accurate and operose investigator, exhibiting very close attention to details. It is difficult to render an account of his achievements, as they extended over almost the entire field of chemistry, and produced reforms of great importance. And one must not forget that the laboratory in which Berzelius accomplished his famous researches was small and imperfectly equipped. To give Wöhler's description of his first visit to it, no water, no gas, no hoods, no oven were to be seen. A couple of plain tables, a blowpipe, a few shelves with bottles, a little simple apparatus, and a large water barrel, whereat Anna, the ancient cook of the establishment, washed the laboratory dishes, completed the furnishings of this room, famous throughout Europe for the work which had been done in it. In the kitchen which adjoined, and where Anna cooked, was a small furnace and a sand bath for heating purposes. Berzelius introduced many improvements in analytical chemistry. It was he who first employed far smaller amounts of substances than the large quantities recommended by Klaproth, who introduced the spirit lamp, which bears his name, thereby rendering the incineration of filter paper and the ignition of precipitates facile, and who worked out many new methods of analysis. Among the latter were his plan of decomposing silicates by the aid of chlorine. He enriched mineralogy by many analyses of minerals and mineral waters, and in a number of these, for example, those of platinum ores, he devised new methods of separation. Berzelius was the first to characterize minerals as being in every respect chemical compounds, and he classified them similarly to substances prepared artificially. He was also able to demonstrate that the doctrine of chemical proportions, and consequently the atomic theory, was applicable to minerals. The close attention which Berzelius gave to details resulted in the discovery of selenium, 1817, thuria, 1828, and in conjunction with Heisinger and independent of Klaproth, he discovered ceria, 1803. He also discovered many new chemical compounds, among which were the compounds of selenium with hydrogen and oxygen, and some molybdenum compounds, isolated the elements silicon, 1810, zirconium and tantalum, 1824, and extended the knowledge of the platinum metals. Passages in the work of Berzelius indicate that he regarded the firm establishment of the doctrine of chemical proportions, and in conjunction with this, the determination of the atomic weights of the elements and the constitution of chemical compounds as his main task. To quote from his Lehrbuch der Chemie, 5th edition, "I resolved to make the analysis of a number of salts, whereby that of others might become superfluous. I soon convinced myself, by new experiments, that Dalton's numbers were wanting in that accuracy which was requisite for the practical application of his theory. I recognized that if the newly arisen light was to spread, it would be necessary to ascertain with the utmost accuracy the atomic weights of all elementary substances, and particularly those of the more common ones. Without such work, no day would follow the dawn. This was therefore the most important object of chemical investigation at the time, and I devoted myself to it with unresting labor. After work extending over 10 years, I was able, in 1818, to publish a table which contained the atomic weights, as calculated from my experiments, of about 2,000 simple and compound substances. In the years 1812 to 1816, Berzelius investigated the stages of oxidation of most of the metals and metalloids then known, and by determining the composition of these oxides, confirmed the law of multiple proportions. His analytical work greatly surpassed that of Dalton, and in the rules established for his guidance in deciding the number of atoms in a given compound or molecule, he exhibited a far greater knowledge. Still, his rules were, in some respects, arbitrary and unsatisfactory. He took oxygen equals 100 as his standard, giving as his reason for this preference the following. To refer the other atomic weights to that of hydrogen offers not only no advantages, but has in fact many inconveniences, seeing that hydrogen is very light and is seldom a constituent of inorganic compounds. Oxygen, on the other hand, unites all the advantages in itself. It is, so to speak, the center point round which the whole of chemistry revolves. This view is again at the present time held by many chemists, who take 16 as the atomic weight of oxygen, and base the atomic weights of all the other elements upon this number. Berzelius began his work at the time when Wollaston was attempting, by his use of the term equivalence to eliminate the question of atoms. Thomson was employing the standard oxygen equals 1, considering that this number would give more of the atomic weights as whole numbers, and failing to perceive that the law of volumes had any particular significance from the atomic standpoint. Berzelius, however, perceived in the law of volumes a corroboration of the atomic theory, and allowed himself to be guided by it in his views upon the number of atoms in chemical compounds, and consequently upon the numerical values of the atomic weights. His volume theory contained the attempt to combine Gay-Lussac's law with the atomic theory. He set forth the atomistic view, which he had himself put into shape under the influence of the law of volumes, definitely and conclusively in 2 papers. He started with the assumption that in the case of every simple substance, when it was in the gaseous form, 1 volume corresponded with 1 atom, and therefore made use of the designation volume atoms for those smallest particles. Wherever it was practicable, he attempted to measure the volumes of the combining substances, and from these deduced the atomic numbers. The analysis of the compound, in which the volumes of the elementary constituents were known, led him to the true determination of the atomic weights of the latter. For example, from the fact that water consists of 2 volumes of hydrogen and 1 of oxygen, he deduced the atomic composition of water, which holds at the present day, together with the relative atomic weights of oxygen and hydrogen. And from the mode of formation of carbonic oxide and carbonic acid, he arrived at the true composition of these compounds, and at the atomic weight of carbon, and so forth. Still, the use which Berzelius made of Gay-Lussac's law was too limited to free him from the necessity of employing rules for deciding the number of atoms in compounds. In 1818, Berzelius gave a table of atomic weights, which contained values which compare favorably with those of other observers. 9 years later, he published another table, which brought his atomic weights still closer to those now current. The reason given by Berzelius for having, in 1826, many of the atomic weights assigned to the metals in 1818 was as follows. It is known that the oxide of chromium contains 3 atoms of oxygen. Chromic acid, for the same number of chromium atoms, contains twice as much oxygen, which would be 6 atoms, but in its neutral salts, chromic acid neutralizes an amount of a base containing 1/3 as much oxygen as it contains itself, a relation found to hold in the case of all acids with 3 atoms of oxygen, for example, sulfuric acid and sulfates. In order to harmonize the multiple relation between the amount of oxygen in the oxide and in the acid, it is most probable that the acid contains 3 atoms of oxygen to 1 atom of chromium, and the oxide 3 atoms of oxygen to 2 of chromium. Isomorphous with the oxide of chromium are those of manganese, iron, and aluminum. Those also we know to contain 3 atoms of oxygen, and consequently must represent them as containing 2 atoms of the radical. But if the ferric oxide consists of 2 Fe plus 3 oxygen, the ferrous oxide is Fe plus oxygen. But if the ferric oxide consists of 2 ferric plus 3 oxide, the ferrous oxide is ferric plus oxide, and the whole series of oxides, isomorphous with it, contains 1 atom of the radical and 1 atom of oxygen. Thus we see that E. Mitscherlich's law of isomorphism, that compounds of analogous composition and containing the same number of atoms crystallize in the same crystalline form, announced in 1819, and which Berzelius regarded as the most important since the establishment of the doctrine of chemical proportions, was an aid in testing his atomic weight determinations, for according to him, isomorphism indicated similarity in atomic constitution. Berzelius further showed that with the exception of cobalt and silver, the law of specific heat justified the change made in 1826. This law was advanced in 1819 by P. L. Dulong and T. A. Pettit, who, in investigating the specific heats of the metals and other bodies, reached the important conclusion that these were very nearly inversely proportional to their atomic weights. Multiplied by their atomic weights, the specific heats gave a constant quantity. This resulted in the law as stated by them. The atoms of the different elements have the same capacity for heat. It is not difficult to perceive that by means of the specific heat one could readily approximate the true atomic weight, and arrive at a decision as to which of the two or more possible figures represented the true weight. There were exceptions to the law which have been explained only in late years. However, the law was extended to simple chemical compounds, and proved of great assistance after it was more fully understood. Berzelius opposed the acceptance of it at first, in part because it would necessitate a revision of his table of atomic weights, and might endanger the accepted views as to some of the atomic relations. He gradually gave up this position, however, when the law was confirmed by other workers, and more accurate determinations were made than the first ones of Dulong and Pettit. Berzelius substituted for Dalton's geometrical symbols a more convenient system of chemical notation, which, to give his own words, might facilitate the expression of chemical proportions, show briefly and clearly the number of elementary atoms in each compound, and after the determination of their relative weights, present the results of each analysis in a simple and easily retained manner. The atom of each element was represented by the initial letter of its Latinized name, a second letter being added when two elements had names beginning with the same capital. An index number was added when more than one atom was present. A compound was thus represented by placing the proper number of these symbols side by side. Thus H is hydrogen, Cl is chlorine, and HCl is hydrogen chloride. Berzelius assumed the existence of certain double atoms where two atoms of an element occur together. These were indicated by a mark across the symbol. Thus H with a stroke through it, followed by O, was water, or as it is now written, H2O. For convenience sake, an atom of oxygen was often indicated by a point or dot. Thus carbon dioxide, C with 2 dots above it, nitrous acid, N with 4 dots above it, potassium nitrate, K, N with 3 dots above the N. These symbols were a great advance over those suggested by Dalton, which were diagrammatic and quite unpractical. Dalton, however, criticized the system of notation of Berzelius, saying that Berzelius' symbols are horrifying. A young student in chemistry might as soon learn Hebrew as make himself acquainted with them. Berzelius adopted dualism as the basis of his chemical system. He extended the term atom so that it included what he regarded as compound atoms, which were built up of two parts, each of which might be a simple atom or a single simple atom. This was the dual structure, which dominated all his views with regard to chemical phenomena, and far more than a decade held a preeminent position in chemistry. Berzelius seemed to have formed this idea of dualism from his observations upon the volumes of gases. For a certain number of these gases, the equivalent is formed of two atoms. This was true not only of hydrogen, but of nitrogen, chlorine, and others, in the form of vapor. The atomic weights of these bodies represent also the specific gravities, or the weights of one volume compared with one volume of the standard. But since it requires 2 volumes of nitrogen, 2 volumes of chlorine, etc., to form the first stage of oxidation, with oxygen 2 volumes of nitrogen, etc., represent the equivalence of these bodies compared with oxygen. Berzelius considered that these atoms, therefore, were united two and two, and called them the double or compound atoms. A uniform method of considering compounds dualistically became possible to a still greater degree in the light of electrical chemical phenomena, and Berzelius introduced this into chemistry and established it. Davy had inclined to the assumption that electrical processes and the phenomena of chemical affinity arose from a common cause. His electrochemical theory was characterized by the axiom that the small particles of substances which have an affinity for one another only become oppositely electrified upon contact. The researches of Berzelius, however, caused the abandonment of this principle, while otherwise many of Davy's original ideas were retained. Davy advanced ideas as to the manner in which he considered chemical and electrical phenomena to be related, but he never succeeded in producing a theory which might serve as the basis of a chemical system. This was accomplished by Berzelius, and therefore his views are of greater importance in the development of chemistry than those of Davy are. To quote from A. Ladenburg's Lectures on the History of Chemistry, according to Berzelius, it is not only when two substances are brought into contact that electricity is generated, but it is a property of matter, and in every atom two oppositely electrical poles are assumed. These poles do not, however, contain equal quantities of electricity. The atoms are unipolar, the electricity of the one pole predominating over that of the other, and thus every atom, and therefore every element, appears to be either positively or negatively electrical. In this respect, it is possible to arrange the elementary substances into a series, so that each member is always more electronegative than the next succeeding one. Oxygen stands at the top, and is absolutely electronegative, while the other substances are only relatively positive or negative according as they are compared with elements, which come before them or after them in the electrical series. This series does not constitute a table of affinities in the Geoffrey Bergman sense, and it does not express the affinity of the individual substances for oxygen, for example. Berzelius has not forgotten Berthollet's teaching that affinity is not of a constant character, and independent of the physical conditions, as he supposes this unipolarity to be. And he is also well aware that oxygen can be removed from metallic oxides by carbon or sulfur, that is to say, by other electronegative substances. With him, affinity depends principally upon the intensity of the polarity, for example, upon the quantity of electricity which is contained in the two poles. This is variable, however, especially with changes of temperature, and, generally speaking, is increased by furnishing more heat, which explained why certain combinations only occurred at a high temperature. Chemical combinations of the elements or compounds consisted, according to Berzelius, in the attraction of the dissimilar poles of the small particles, and in the consequent neutralization of the different electricities. When positive electricity predominated in the original substance, then an electropositive compound resulted, and vice versa. If the electricities neutralized one another, then an electrically indifferent product was the result. Oxygen, as the most electronegative element, served Berzelius here as the standard by which to determine the kind of polarity of the various elements. Those elements which yielded basic compounds with oxygen, even although only their lowest oxides were basic, were classed as electropositive, and those whose oxides were acids as electronegative. Following this principle, he arranged the simple substances in a series, in which oxygen, as the first member, was followed by the other metalloids, while hydrogen formed the bridge between the latter and the metals, the whole ending with sodium and potassium. Such conceptions formed the substance of his electrochemical theory, which constituted the basis of the dualistic theory of chemical composition. Berzelius established it as follows: if the electrochemical views are accurate, it follows that every chemical combination depends wholly and solely upon two opposite forces, namely the positive and the negative electricities, and that every compound must be composed of two parts, united by the effects of their electrochemical reactions, since there is not any third force. From this it follows that every compound substance, whatever the number of its constituents may be, can be divided into two parts, of which the one is positively and the other is negatively electrical. Thus, for example, sulfate of soda is not composed of sulfur, oxygen, and sodium, but of sulfuric acid and soda, each of which can, in turn, be separately divided into an electropositive and an electronegative constituent. In the same way, also, alum cannot be regarded as immediately composed of its elementary constituents, but is to be looked upon as the product of the reaction of sulfate of alumina as negative element, with sulfate of potash as positive element, and thus the electrochemical view justifies what I have said with respect to compound atoms of the first, second, third, etc. orders. In the year 1819, when Berzelius contributed a complete exposition of his electrochemical theory, he was convinced that all acids contained oxygen. In his view, water assumed in hydrated acids the role of a weak electropositive constituent, and in metallic hydroxides that of a weak electronegative one. The hydrates of sulfuric acid and of cupric oxide, therefore, received the formula H2O.SO3, CuO.H2O. The binary conception, which had already been applied by Lavoisier to acids and bases, and even by Rouelle to salts, thus received the strongest support from the electrochemical theory, and was materially developed as a result. Finally, however, the theory of the oxygen acids, based on the tenet established by Lavoisier, was abandoned by chemists during the second decade of the 19th century, as a knowledge of facts in opposition to it augmented, and at last Berzelius convinced himself of the existence of acids free from oxygen, at which time the unadaptable system of dualism began to decline in favor. It had explained, however, the mysterious chemical force, even though the identification of chemical affinity with electrical polarity was one not justified by the facts at hand, and dominated chemistry for 2 decades. As a result of the efforts of Berzelius, chemistry was now in the possession of a comprehensive theory of chemical reaction, a rational and systematic nomenclature, and a large quantity of experimental data. He was responsible for a solid basis in the laws of constant proportions and multiples, and the table of atomic weights which he published in 1827 was remarkably accurate, the determinations approaching the more exact work of the present time. These contributions equipped chemistry for the period of remarkable extension in the accumulation of data and in the formulation of theory which the past 80 years have witnessed. Mention has been made of the law of de Long and Petit and of the law of Mitscherlich. The exceptions to the former, exhibited by many of the non-metals in a greater or lesser diminution of the atomic heats, have only in some measure been explained in recent years by the proof that the specific heats of such elements vary greatly with the temperature. In the case of simple chemical compounds, a relation was soon found between their specific heats and atomic weights by Neumann in 1831, who said, "I find that for compound substances a simple relation exists between the specific heats and the stoichiometric quantities, and I call stoichiometric quantities the amounts of substances which, as for instance in the case of the anhydrous carbonates, contain the same amount of oxygen, while in the case of sulfur compounds the amount of sulfur is the measure of the stoichiometric quantity. For chemically similar substances, the specific heats are inversely proportional to the stoichiometric quantities, or what comes to the same thing. The stoichiometric quantities of chemically similar substances have the same heat capacity. The investigation of the carbonates first led me to the discovery of this law. Renaud, who extended the empirical basis of the law of constant atomic heat in 1840, while engaged in investigations on the specific heats of compounds, corroborated Neumann's results, but it was reserved for Kopp in 1865 to definitely prove that the connection between the specific heat and the composition of a compound holds in the perfectly simple and general manner enunciated by Petit and Dulong, and that heat capacity is of the nature of an additive property. The law of Mitscherlich was the outgrowth of coordinating physical form with chemical composition, a question which until the time of Eilert Mitscherlich (1794 to 1863) had been attacked entirely from the crystallographic side. In 1801, Abe Hoy (1743 to 1822), the founder of the science of crystallography, produced a system of mineral classification based first on their crystalline character and secondly on their chemical composition. His guiding principle was that every difference in the fundamental form of a crystal implied difference in its chemical composition. This supposed law was supported by numerous facts, but there were also on record well-defined and undoubted exceptions. As far back as 1772, Rome de Lisle had observed that copper sulfate and ferrous sulfate crystallize from a mixed solution in the form of the latter, and in 1788 Klaproth established the chemical identity of rhombohedral calcite and rhombic aragonite. Mitscherlich was the first to recognize definitely the relation between crystalline form and chemical constitution. He explained the occurrence of isomorphous crystals in substances of different nature by demonstrating that they possessed a similar chemical composition. For instance, he found on examining the salts of phosphoric and arsenic acids that only those of analogous composition and containing equal amounts of water of crystallization were isomorphous. His subsequent investigations of selenites and sulfates, of the isomorphism of magnesium and zinc oxides, and of iron, chromium, and aluminum salts, confirm the intimate connection existing between crystalline form and chemical composition. Primarily after making these observations, Mitscherlich was of opinion that isomorphism depended chiefly on the number of the elementary particles, but he soon became convinced that the chemical nature of these had also to do with it. The importance of Mitscherlich's work met with immediate recognition, and data in support of the law were quickly accumulated. With regard to its deductive application, it is employed for purposes of classifying the elements and of atomic weight determinations. From the isomorphism of the salts of an acid of selenium with sulfates and chromates, Mitscherlich was led to the discovery of that acid, selenic acid, and his recognition of the isomorphism with potassium sulfate of the green potassium salt of a manganese acid, and of the isomorphism with potassium perchlorate of the red potassium salt of another manganese acid, has revealed the true composition of these two acids. It has been mentioned how the isomorphism of sulfates and chromates induced Berzelius to modify the formula of basic chromic oxide, and a subsequent halving of the atomic weights of most of the metals. He still adhered to the idea that the amounts of the elements contained in equal gaseous volumes were proportioned to their atomic weights. However, this assumption was soon invalidated by the remarkable results of an investigation which exercised such a marked influence on the views of many chemists that it must be described at this point. This was the work of Jean-Baptiste André Dumas, 1800 to 1884, on the atomic weights. In 1827, Dumas published a paper entitled Memoir on Some Points of the Atomistic Theory, in which he stated the object of these researches is to replace by definite conceptions the arbitrary data on which nearly the whole of the atomic theory is based. Dumas showed that the conception of the equivalent cannot be employed as the basis of a system, because it loses its significance when it is extended further than to acids, to bases, and to other substances which closely resemble each other, oxides and sulfides, and particularly that it becomes quite obscure when the attempt is made to identify the equivalent with the combining weight, since very many substances can combine in several proportions. For example, 8 parts of copper are combined with 1 part of oxygen in cuprous oxide, while for 8 parts of copper, 2 parts of oxygen are contained in cupric oxide. Calculated from these numbers, the equivalent of copper, referred to that of oxygen as unity, is 8 or 4. In order to confirm his ideas, Dumas adopted Avogadro's hypothesis as a basis, and devised in 1827 an admirable method for the determination of vapor densities. He determined that the determination of the density of vapors and gases, elementary as well as compound, was necessary to elucidate the question of the composition of the elementary molecule. But his practice did not agree with his theory. He and his contemporaries argued from the premise that the vapor densities of elements are proportional not only to their molecular weights, but also to their atomic weights, which of course involved the unwarranted assumption that all elementary gaseous molecules are composed of the same number of atoms, for example, of 2. He was successful in elaborating a method for conducting determinations of this kind at high temperatures, and used it for ascertaining the relative densities of the vapors of iodine, phosphorus, sulfur, mercury, etc. His results, from which he anticipated confirmation of his views, induced him to abandon them. He found the density of phosphorus vapor to be twice as great, and that of sulfur vapor to be 3 times as great as he had previously assumed, while that of mercury vapor was only 1/2 of what he had supposed. In view of these facts, he began to doubt. In fact, he declared that even the simple gases do not contain, in the same volume, the same number of chemical atoms. According to him, the assumption could still be made that there is the same number of molecular or atomic groups present in equal volumes of all gases, but that this is only a hypothesis, which cannot be of service. Dumas was obliged to admit that Gay-Lussac's law, when applied in the way he had applied it to the determination of atomic weights, furnished erroneous results. Hence he believed that it could not be employed for this purpose, and he abandoned Avogadro's hypothesis. Berzelius also was able no longer to maintain the law of volumes, so far as its application in atomic weight determinations was concerned, and confined his proposition to the permanent gases. The reform which Dumas had aimed at was, therefore, without result, and, if anything, he had merely introduced obscurity into the atomic weight system of Berzelius. As a result, chemists regarded Avogadro's law with indifference. The law of de Long and Petit was shown also to have some unexplained exceptions, and Mitscherlich, by his further discovery of dimorphism, which had thrown much doubt upon his law of isomorphism. Consequently, at the close of the 30th year of this century, the atomic theory was regarded by many chemists as either disproved or excluded to a very hypothetical position. Even Gay-Lussac and Liebig doubted whether it was possible to determine the relative weights of the atoms with certitude, and would have left the atomic weights out of consideration, substituting the establishment of equivalents. Leopold Gmelin, however, was at the head of the movement to supplant the system of Berzelius by the equivalence of Wollaston. According to Gmelin, there was no strict distinction between mixtures and compounds, and this demonstrates that he did not believe in the real existence of atoms. 2 substances, especially when they possess only a weak affinity for each other, can combine, according to him, in an infinite number of proportions, but the greater the affinity, the greater is their tendency to combine in few proportions only. These proportions then stand to each other in simple relations. There can, therefore, be assigned to every substance a certain weight in which it combines with definite weights of other elements. This weight is the stoichiometric number, the chemical equivalent, the mixture weight or atomic weight, and so on. Compounds are composed in such proportions that one mixture weight of one substance is united to a quarter, a third, a half, 2/3, 3/4, 1, 1.5, 2, 2.5, 3, 4, 5, 6, 7, or more mixture weights of the other. According to Gmelin, Gay-Lussac's law runs as follows: one measure of an elastic fluid substance combines with 1, 1 1/3, 2, 2.5, 3, 3.5, and 4 measures of the other. Gmelin's table of equivalents is well known. It ran H equals 1, O equals 8, S equals 16, C equals 6, etc. Water was written HO, and in formula generally the attempt was made to replace by simplicity what they had lost in conception and in purpose. As Ladenburg observes, chemistry was to become a science of confined observation, indeed almost to description alone. Skill in manipulation was all that was required. Speculation was banished as dangerous. It had come to this, then. Inorganic chemistry, in connection with physics, had not been able to maintain the conception of the atom. By the assistance of the growing science of organic chemistry, however, the theories of chemistry were rescued and advanced, and the atomic theory was reintroduced. But reference must be made to the status of the atomic theory in England at this time. In England, in the 1833 edition of Edward Turner's Elements of Chemistry, the atomic theory is referred to as follows: in consequence of the satisfactory explanation which the laws of chemical union receive by means of the atomic theory, it has become customary to employ the term atom in the same sense as combining proportion or equivalent. A discovery of great importance was made in 1834, when Michael Faraday, 1794 to 1867, professor in the Royal Institution of London, who had been engaged in studying quantitatively some changes produced by the passage of a current of electricity, detected the connection which existed with the combining numbers of the elements, and thereby deduced his law of electrical equivalence. Faraday made the observation that the same galvanic current decomposed electrolytes, for example water, hydrochloric acid, and metallic chlorides, in such a manner that equivalent amounts of hydrogen or metal were separated at the negative pole, and the corresponding quantities of oxygen or chlorine at the positive. He classified these facts together under the title of the law of definite electrolytic action. In the determination of electrochemical equivalents, he perceived a sure auxiliary means for adjusting chemical atomic weights in doubtful cases. End of section 15. Recording by Lawrence Trask. Mount Vernon, Ohio. InterfaceAudio.com.
Section 16 of the Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 4, edited by Francis Rolt-Wheeler. Chemistry. Chapter 12. The Development of Organic Chemistry. Lavoisier showed that organic substances were composed principally of carbon, hydrogen, and oxygen, together with nitrogen and sometimes sulfur and phosphorus. He had observed that an element was capable of forming more than one oxide, and from this he concluded that organic radicals deported themselves similarly. He consequently regarded sugar as the neutral oxide d'un radical hydrocarboneux, and oxalic acid as its higher oxide. He even hazarded the conjecture that the fatty oils, which he considered to be hydrocarbons, might actually constitute organic radicals in the free state, and might, by oxidation, be converted into neutral oxides and vegetable acids. Among Lavoisier's other investigations in organic chemistry, his research on the process of vinous fermentation is worthy of mention. He expressed the results in the form of the equation 3 ounces 7 gross of water plus 2 pounds 8 ounces sugar produce, on fermentation, 1 pound 7 ounce 5 gross 18 grains of alcohol plus 1 pound of carbonic acid. In this equation, says he, there is only sugar whose constitutional parts are unknown to me. I know the composition of water, of alcohol, and of carbonic acid, and nothing is easier than to substitute these values in the equation established and then deduce the constituent parts of sugar. However, Lavoisier did not regard organic chemistry as a separate division of the science. He classed all acids together, and like Lemery in 1675, subdivided them into mineral, vegetable, and animal acids. With a few exceptions, the immediate followers of Lavoisier followed the same plan, and the division of chemistry into inorganic and organic chemistry was not generally adopted until it became clear that several compounds occur both in the vegetable and animal kingdom, and therefore that no difference existed between vegetable and animal chemistry. In this connection, the work of M. E. Chevreul, 1786 to 1889, should be emphasized, as it was his investigations which demonstrated that many of the fats and acids and other substances occurring in both kingdoms were identical. However, for some time subsequently, considerable doubt prevailed as to the boundary of inorganic and organic chemistry. One reason for this was that inorganic substances, as well as some which had to be considered as organic, gave on analysis numbers which demonstrated that their composition was in accordance with the laws of constant and multiple proportions. As Berzelius stated in 1811, the majority of organic substances, however, appeared not to obey these laws, and consequently he undertook to decide this question by the analysis of a large number of them. After years of labor and after improving the appliances and methods of organic analysis, he finally obtained results which proved that although most organic compounds possessed a much more complicated composition than the mineral compounds, yet they obeyed the laws of constant and multiple proportions. He adopted the views of Lavoisier and said, after we got a clearer insight into the difference existing between the products of organic and inorganic nature, and the different manner in which their ultimate components are united with each other, we find this difference consists really in the fact that in inorganic nature, all oxidized bodies contain a simple radical, while all organic substances are oxides of compound radicals. The radicals of vegetable substances consist generally of carbon and hydrogen, and those of animal substances of carbon, hydrogen, and nitrogen. In his ideas as to these radicals, he was especially influenced by the research of Gay-Lussac upon cyanogen, in which he showed that this radical played the role of an element. Attempts were multiplied to discover the various organic substances having complex groupings of atoms which performed as elements. Thus, Gay-Lussac regarded alcohol as ethylene and water. Dobereiner considered oxalic acid as carbonic acid and carbon monoxide. As Berzelius pointed out, this was opposed to the electrochemical theory, and there was danger of confusion and error. The search for the proximate constituents in organic substances induced a rapid development of the science, leading especially to many efforts at definitely determining the chemical constitution of these bodies. One of the most important of the discoveries in the third decade was that of isomerism. This was viewed as an error by chemists at first, so little prepared were they to believe that bodies similarly composed could be chemically and physically different. It was in the year 1823 that Liebig announced that his analysis of silver fulminate yielded the same results as Wöhler had found in the preceding year for his silver cyanate. He was confident that his figures were correct and believed that Wöhler must have made a mistake. A careful repetition of the analyses showed him that both were correct, and so it was proved that two bodies, totally unlike, could and did have the same composition. Gay-Lussac saw that the only explanation of this lay in the different mode in which the elements were combined. In 1826, Berzelius reported on Liebig's fulminate of silver as follows. This substance has been made the subject of a new joint investigation by Gay-Lussac and Liebig, and the result is of the utmost interest. Fulminate of silver dried at 100 degrees loses all its water, and in 3 experiments they found between 16.87 and 17.38% cyanogen, the mean being 17.16%. The silver oxide was separated by hydrochloric acid and was found to be 77.528% of the weight of the salt. These quantities add up to 94.688%. The deficiency is only 5.312%, a quantity absolutely equal to that of the oxygen in the silver oxide. Hence, the salt was composed of 77.528% of silver oxide and 22.472% of cyanic acid. But this result is identical with that obtained by Wöhler in his analysis of silver cyanate, in spite of which agreement between the analytical results, the two substances have not the same properties. The chief difference is that Wöhler's cyanate of silver, when heated by itself, does not explode, but only burns with moderate intensity. And further, that when decomposed by acids, it is completely changed into carbonic acid and ammonia, while fulminic acid has explosive properties and gives ammonia and prussic acid when its salts are decomposed by oxyacids. These facts point unquestionably to a difference in composition. Jahresbericht, 1826. In 1825, Michael Faraday announced the results of his work on the hydrocarbons from oil gas, when he demonstrated the existence of butylene, an isomer of ethylene. In 1827, Berzelius commented on this discovery in part as follows. The two gases are of like constitution, but a given volume of the one contains twice as many simple atoms as does the other, and this produces a certain dissimilarity in physical and chemical character. Definite knowledge concerning this phenomenon would be of such significance in the doctrine of the composition of vegetable and animal bodies, and would have so important a bearing on organic chemistry, that it must not be accepted as demonstrated until its truth has been subjected to the most severe proof. It is not my intention to dispute the possibility or the actuality of such a fact, but I maintain that before accepting it with confidence, the relation observed by Faraday must be found in a number of other cases. In 1832 and 1833, Berzelius formally adopted the addition to the doctrine of chemical composition rendered necessary by these observations, and suggested his classical classification of the new phenomena, concluding as follows. But since it is requisite that we should be able to express our conceptions by definite and appropriately chosen terms, I have proposed to call substances of the same composition and of different properties isomeric, from the Greek isomeri, composed of equal parts. The general designation isomerism has since then been retained. Berzelius soon saw himself necessitated to define more strictly the meaning to be attached to this word, and therefore he distinguished between polymerism and metamerism as special cases of isomerism. The ideas of Berzelius with regard to the probable cause of isomerism in organic compounds are clearly shown in many of his statements. In his view, isomeric compounds are those in which the atoms of the elementary constituents have grouped themselves differently into compound radicals. The isomerism of compounds in itself presupposes that the positions of the atoms in them must be different, and it appears that he considered it possible to determine the mutual relations of the atoms in their compounds. At the period that is now reached, to quote Karl Schorlemmer, we find Berzelius laying stress again on a difference between organic and inorganic substances, first pointed out by Gmelin, 1817, and according to which the latter, but not the former, could be prepared artificially. Berzelius was of opinion that within the sphere of living nature, the elements obeyed laws totally different from those ruling in inanimate nature. It was then commonly supposed that the compounds found in plants and animals were produced by the action of a so-called vital force, and that although they might be changed into other compounds, none of them could be prepared artificially from their elements. Thus grape sugar, a compound widely distributed in the vegetable kingdom, by fermentation yielded alcohol, which could be converted into ether, acetic acid, and many other compounds, and all of these were considered to be organic, as none of them could be prepared synthetically. It was Friedrich Wöhler's synthesis of urea which finally removed this obstacle to the growth of organic chemistry. In 1828, Wöhler made the discovery that cyanate of ammonia, which was regarded as an inorganic compound, could be converted into urea, a substance hitherto known only as a product of animal metabolism. This was the first synthesis of an organic compound, and is generally referred to as marking the beginning of scientific organic chemistry. Yet it remained an isolated fact for a long time, and failed to shake the belief in a vital force, a belief which was maintained during the lapse of many years. In 1830 and 1831, Liebig perfected and simplified the operations for the ultimate analysis of organic compounds, and this to such a degree that his processes have not required any essential alterations to fit them to modern requirements. These perfected methods enabled Liebig to carry out his famous researches in Gießen, work which renders a brief biographical mention of this master fitting. Justus Liebig was born at Darmstadt on May 12, 1803. The fact of his father being a dealer in dyestuffs brought him early into contact with laboratory problems. At 15 years, he was sent to a neighboring town to learn the business of apothecary. But pharmacy was not chemistry, as Liebig was beginning to understand it, so he entered the University of Bonn. Here was certainly change, much ingenious contemplation, but no chemistry. He traveled to Erlangen, where he heard lectures, read books, and at 19 obtained a degree. Then his chance came. His ability being made known to the Grand Duke of Hesse-Darmstadt, he was provided with the means of studying in Paris. There worked closely giants Gay-Lussac, Thénard, Chevreul, Vauquelin, and Dulong. Nor was it long before Liebig was received into the laboratory of Gay-Lussac. Liebig had meanwhile won the appreciation of Humboldt. His was a personality that inspired immediate and warm friendships. Of slender form was he, a friendly earnestness in his regular features, great brown eyes with shady eyebrows, which attracted one instantly. It was Humboldt who, in 1824, brought him as extraordinary professor of chemistry to Gießen. 2 years later, he was elected to the ordinary professorship, which office he held for the next 26 years. The dull little town of Gießen became famous. The fires of Liebig's laboratory acted as a beacon light, attracting chastened spirits from the four quarters of the civilized world. For it was not long before the master had roused the Darmstadt government to build a laboratory where all might come and seek and find. And the movement spread. Liebig, through his pupils, tinctured the world. There were other governments than that of Darmstadt, and soon there were other public laboratories than that of Gießen. In 1845, Liebig was created baron. In 1852, he accepted a call of the Bavarian government to the Munich professorship of chemistry. Warmly appreciated by the Bavarian court, entering into the social and philosophical life of the university town, courted by all the scientific circles of Europe, yet continually fighting weakening health, Liebig passed the remainder of his life in Munich. He died in 1873. Liebig devoted his full powers of mind to organic chemistry, but did not neglect inorganic chemistry, as his work on the compounds of silicic acid, alumina, and antimony clearly shows. His work in physiological and agricultural chemistry rendered him a general benefactor of mankind, and to quote A.W. von Hoffmann, if we sum up in our minds all that Liebig did for the good of mankind, in industries, in agriculture, and in the laws of health, we may confidently assert that no other man of learning in his course through the world has ever left a more valuable legacy behind him. Writing in 1810, Gay-Lussac and Thénard gave, as a reason for the slow progress of animal and vegetable chemistry, the inadequacy of the methods of organic analysis. In their Recherche physico-chimique, which appeared in 1811, they gave an exhaustive description of a new method of organic analysis, the results of analyses of sugar, starch, gum arabic, milk, sugar, wood, and mucic, oxalic, tartaric, and acetic acids, as well as of oils, resins, and waxes, and the following generalizations made from the results of their work. 1. A vegetable substance is always acid, when it contains more oxygen than will form water with the hydrogen. 2. It will be always resinous, oily, or alcoholic when it contains less oxygen than suffices the hydrogen. 3. The body will be neither acid nor resinous, but analogous to sugar or ligneous fiber when the oxygen and hydrogen are present in just the proportions to form water. This classification was, of course, of little service, but it was suggestive, and although no proper classification was possible at this time, the interpretation of Gay-Lussac and Thénard gave a stimulus to the study of the constituents of organic compounds. Berzelius explained in 1819 that his electrochemical theory could not be extended to organic chemistry because under the influence of the vital force, the elements there possessed entirely different electrochemical properties. In decay, putrefaction, fermentation, etc., he observes phenomena which he regards as demonstrating the tendency of the elements to return to their normal condition. He did not, at that time, as yet consider it possible to regard all organic substances as binary groups. Dualism was, indeed, extended as far as possible. The oxygen compounds were looked upon as oxides of compound radicals, which, however, do not exist free, but are wholly hypothetical, a mode of regarding the matter which was especially applicable to the acids. In 1838, Liebig defined a compound radical enunciating 3 characteristics and making use of cyanogen as an instance. We term cyanogen a radical because 1. It is the unchanging constituent of a series of compounds. 2. Because it is capable of replacement in these by simple substances. And 3. Because in those cases where it is combined with one element, this latter can be exchanged for its equivalent of another element. At least 2 of the conditions here adduced had to be fulfilled in order that an atomic complex might be stamped as a radical. The existence of these conditions, moreover, could only be established by the most minute investigation of the chemical behavior of organic bodies. That is to say, the nature of the radicals assumed in the latter could only be arrived at from the study of their reaction and decomposition products. This radical theory aroused considerable interest, and chemists of eminence were attracted to the task of investigating the constituents of compounds related to one another. Thus, the research of Bunsen upon cacodyl compounds, which formed one of the strongest supports of the theory, may be mentioned. Robert Wilhelm Bunsen, 1811 to 1899, enriched every branch of chemistry by his valuable researches. He created the gas analysis methods of today. With Kirchhoff, he developed spectrum analysis into one of the great branches of today, and in his investigations in analytical and inorganic chemistry and in geochemistry, he showed himself a pioneer in the science. Bunsen's researches on the cacodyl compounds resulted in the proof that the so-called alkersin, the product of the distillation of acetate of potash with arsenious acid, contained the oxide of an arsenurated radical, arsenic 2, carbon 4, hydrogen 12. Hydrogen equals 1, carbon equals 12, arsenic equals 75. This radical remaining unchanged in a long series of reactions of that oxide, and being even itself capable of isolation. This compound element, containing arsenic, an unusual constituent of organic bodies, was thus shown to be a true radical. Inasmuch as the radical was supposed to be constituted of atoms held together by stronger forces than those which united the group to other atoms, it attained a real significance in the minds of chemists, and as the dualistic theory and the theory of compound radicals became more solidly entrenched in chemistry, they rendered the atomic theory, on which of course they were founded, an essentiality, and even after dualism was discredited, the only changes were in the ideas as to the nature of the ultimate particles, or atoms. About this time, however, facts became known which could not be brought into accord with the radical theory, and as a result, doubts were expressed as to the theory of dualism. But it was the discovery of the principle of substitution which actually caused this theory to succumb, and paved the way for the so-termed unitary theory. The conception of equivalence might have led to that of replacement or substitution, since the quantities of 2 acids were equivalent when they saturated the same quantity of a base. The acid in a neutral salt could thus be replaced by its equivalent without the neutrality being interfered with. The word replacement received further justification after Mitscherlich had studied the phenomena of isomorphism. It could then be said that certain elements in a crystal might be replaced by others without alteration of the crystalline form. Such substitutions possessed the peculiarity, however, that they were not connected with any proportions by weight, and it may thus appear all the more remarkable that they should render important assistance in the determination of atomic weights. The hypothesis underlying the phenomena of isomorphism was that one atom could only be replaced by one other, that is to say, that the numbers of the atoms in isomorphous compounds must be identical. Since chemically similar substances had alone been compared, an extension of the prevailing views, based on the phenomena of isomorphism, would have been quite possible, but this class of phenomena had never led to any attack upon the system. In the bleaching of wax by means of chlorine, Gay-Lussac had observed that for every volume of hydrogen eliminated, an equal volume of chlorine was taken up. He had also found the same thing in the action of chlorine on hydrocyanic acid. In the course of their investigation of the benzoyl compounds previously referred to, Wöhler and Liebig, when acting with chlorine upon bitter almond oil, had discovered benzoyl chloride, and they expressly remarked that this substance is produced from the bitter almond oil by 2 atoms of chlorine taking the place of 2 of hydrogen. In the year 1834, Dumas, apropos of an investigation on the mutual action between chlorine and oil of turpentine, but more especially of his work upon the production of chloral from alcohol, condensed into 2 empirical rules the facts with regard to substitution, for which he proposed the designation metalepsy, that is, exchange, metalepsis. These were not intended to comprise a theory of substitution, as his first utterances on the subject show, but only to give expression to the facts. They were as follows. When a compound containing hydrogen is exposed to the dehydrogenizing action of chlorine, bromine, or iodine, it takes up an equal volume of chlorine, bromine, etc. for each atom of hydrogen that it loses. If the compound contains water, it loses the hydrogen of this without replacement. The second of these rules was deduced from the transformation of alcohol into chloral, and was thus intended to explain the mode of formation of the latter and at the same time to support Dumas' view of the constitution of alcohol, the latter being regarded by him as a compound of ethylene and water. By means of various examples, Dumas further endeavored to prove the general validity of the laws which he advanced. In establishing the correct composition of the Dutch oil, he pointed out that the chloride of carbon obtained from it by means of chlorine and examined by Faraday supplied a new argument in favor of the accuracy of his views. He also found similar support in the action of chlorine on hydrocyanic acid, on bitter almond oil, etc. However, he was unsatisfied with this and extended his statement to one of greater significance, regarding oxidations as cases of substitution, as, for instance, the conversion of alcohol into acetic acid. While Dumas limited himself at this time, 1835, to condensing the known facts into the above laws, Auguste Laurent, 1807 to 1853, a pupil of Dumas, went further and considered the nature of the compounds resulting from substitution and made a comparison of them with the original ones. He was thereby induced to enunciate the proposition that the structure and chemical nature of organic compounds are not materially changed by the entrance of chlorine and the separation of hydrogen. This law is the core of the substitution theory proper, of which Laurent was the propounder. Laurent endeavored to give expression to the observed facts and to the hypotheses based upon them in the so-called nucleus theory. This theory is of importance in the science, although it never obtained any general recognition in it, because chemists have adopted, if in another form, many of the ideas embraced by it, and also because it was adopted by Gmelin as the basis of the organic portion of his excellent handbook. On this account, the chief points of Laurent's doctrines will be stated. According to Laurent, all organic substances contain certain nuclei, which he calls either fundamental, radico-fondamentaux, or derived. The former are compounds of carbon with hydrogen, in which the mutual proportion of the number of the atoms is a simple one, 1 to 2, 3, 4, etc., 2 to 3, etc. For any definite proportion, several nuclei exist which are polymeric among themselves. Besides, these fundamental radicals are so chosen that the hydrogen and carbon atoms contained in them occur in pairs. The derived nuclei, radicaux dérivés, were produced from the original nuclei either through the substitution of hydrogen by other elements or by the addition of other atoms. This theory manifestly sprang from the old radical theory, but with an important change, namely, the radical here is not an unchanging group of atoms, but it is a combination which can be changed through the substitution of equivalents. It is but a step in the evolution of the modern theory as seen in the benzene nucleus. The nucleus theory was regarded as unscientific by Liebig, and Berzelius opposed it, but the latter was moved before long by Malaguti's investigation of the simple and compound ethers, in which he demonstrated that the chlorine atoms again played the part just as the hydrogen atoms they had displaced, and as Armitage observes in his History of Chemistry, he saw that here was the thin edge of a most potent wedge which, unless immediately removed, might break down the whole fabric of that chemical theory he had spent so much on building. Before Laurent, in conjunction with Gerhardt, had again brought forward his ideas in a more perfect form, Dumas entered the lists to do battle against the radical theory, and with this, against the dualistic idea in general. His beautiful discovery of chloroacetic acid afforded him the immediate occasion for this, and he now gave in his adhesion to Laurent's opinions, which formerly he would have nothing to do with. By the action of chlorine in sunlight upon acetic acid, Dumas had obtained a crystalline substance whose composition could be expressed by the formula carbon 4, chlorine 6, hydrogen 2, oxygen 4, and which could, therefore, be regarded as acetic acid, carbon 4, hydrogen 8, oxygen 4, in which 6 atoms or volumes of hydrogen were replaced by 6 atoms of chlorine. The interesting and important part of this reaction lay in the properties of the new compound, which Dumas called chloroacetic acid. This acid had the same saturating capacity as acetic acid, so that Dumas was able to assert that by the entrance of chlorine in place of the hydrogen, the chief character of the compound was not altered, or, as he expresses himself, that in organic chemistry there are certain types which persist even when an equal volume of chlorine, bromine, or iodine is introduced into them in place of the hydrogen which they contain. He was thus led to the same view which had already been taken up by Laurent, but his theory of types, 1839, was hardly a mere application of the views of Laurent. The principal propositions of this theory were as follows. 1. The elements of a compound body can, in many cases, be replaced by equivalents of other elements or of compound bodies which play the part of simple ones. 2. If such a substitution occurs equivalent for equivalent, the compound in which the replacement has taken place retains its chemical type, and the element or group which has been taken up plays in it the same part as the element which has gone out. The term chemical type failed to satisfy Dumas, however, and he permitted it to merge into that of mechanical type, which included all compounds which might be supposed to be formed from one another by substitution, even though they differed in properties. Berzelius could not accept these views, and when Dumas characterized his electrochemical theory as erroneous, an embittered discussion ensued which lasted for years. The proposition of Dumas that every chemical compound forms a complete whole and cannot therefore consist of two parts, that its chemical character is dependent primarily upon the arrangement and number of the atoms, and in a lesser degree upon their chemical nature, proclaimed a decided unitarism and was therefore violently opposed by Berzelius. Berzelius sought to get over the difficulties which the substitution of hydrogen by chlorine and other elements involved by arguing that compounds formed in this manner must have a constitution different from that of the original ones. But here he entered upon dangerous ground, and was thereby led, prudent investigator as he was, into the most utter contradictions of the principles which he had formerly held to be inviolable. Facts now increased which went to demonstrate the correctness of the theory of substitution, and in 1842 Melsens found that by the action of potassium amalgam on a water solution of trichloroacetic acid, its chlorine was completely replaced by hydrogen, acetic acid being reproduced. This was a discovery of the greatest import, as it showed inverse substitution was possible, yet it did not shake Berzelius's faith. He merely decided to look upon acetic acid in the same way as its chlorine derivative, that is, as a copulated oxalic acid with the copula methyl carbon 2H3, formulating the two compounds thus: carbon 2 hydrogen 3 plus carbon 2 oxygen 3 dot hydrogen oxygen acetic acid, carbon 2 chlorine 3 plus carbon 2 oxygen 3 dot hydrogen oxygen chloroacetic acid. This was practically giving up the fight, as by it he acknowledged that the parling or copula could undergo substitution, and that its exact nature did not have a predominating influence in determining the nature of the compound into which it entered. Yet Berzelius remained an opponent of the theory of types until his death in 1848, and his adherents experienced great difficulty in reconstructing radicals anew from his copulae after his death. In 1845, A.W. Hoffman discovered the substituted anilines and observed that it appeared without doubt that chlorine or bromine could assume the role of hydrogen in organic compounds, taking their electronegative character with them into the new compounds. Liebig commented on Hoffman's report as follows: "The author appears to have definitely proved that the chemical nature of a compound does not in any way depend upon the nature of the elements contained in it, as is assumed by the electrochemical theory, but entirely on their arrangement." Liebig now turned to the unitary theory and opposed Berzelius's attempted explanations. Other prominent chemists, too, became his opponents, and yet, in spite of the slight regard in which the radical theory was held in many quarters, it soon became evident that, for the investigation of chemical constitution, the assumption of radicals, which had been displaced by the theory of types, was indispensable. In the fifth decade, a fusion of the radical theory with the doctrine of types occurred on the unitary side, and as a result of the work of Auguste Laurent and Charles Gerhardt, 1816 to 1856, the older theory of types was transformed into the new theory. In 1839, Gerhardt published his views on the process which occurs when an element is replaced by a group of atoms. In his opinion, it was not a substitution, but a union of two residues to a unitary whole, and not an articulated binary compound. He termed these groups of atoms les restes or les restants, and later developed his theory of residues, according to which a residue could have the composition of a compound radical, but was not present as such in a compound. His conception of radicals soon replaced the older views, and its introduction into the theory of types induced a fusion of both theories. The first advance in this direction was made in 1849, when C.A. Wurtz, 1817 to 1884, discovered the compound ammonias. Hoffman found another method of preparing the bases discovered by Wurtz, and the typical view of these bases was first arrived at by means of his investigations. He showed that in the amine bases, as well as in aniline, the two hydrogen atoms of the amide could be replaced by alcohol radicals. A.W. Williamson, 1824 to 1904, then demonstrated that in a similar manner the alcohols and their ethers could be referred to the type water. He also pointed out that acetic acid must have a constitution similar to that of alcohol, and proposed to call the radical carbon 2 hydrogen 3 oxygen, obtained from ethyl by oxygen substitution, authal. Gerhardt, employing a reaction similar to that by which Williamson had prepared the ethers, discovered the anhydrous acids, and chemists began to attempt to find among the more simple inorganic compounds other types for organic compounds, thereby giving rise to Gerhardt's theory of types. According to this theory, the organic compounds of known constitution can be classified under four types, namely hydrogen, hydrochloric acid, water, and ammonia. For example, the hydrocarbons, aldehydes, and the acetones or ketones were classed in the first type, the halides, chlorides, bromides, iodides, and fluorides in the second, the alcohols, ethers, monobasic acids, and sulfides and hydrosulfides in the third, and the amines were placed in the fourth type. The general arrangement and the comprehensive character of Gerhardt's system leave nothing to be desired. even although views have been considerably changed and cleared up since that time, and although one is compelled, from the modern standpoint, to look upon the types as insufficient, still, Gerhardt's services to chemistry can never be questioned. Unfortunately, he did not live to witness the reception which was extended by many chemists to the views laid down by him in the fourth volume of his Lehrbuch der organischen Chemie. The type theory was particularly extended by the assumption of mixed types, which was intended to render clear the relations of many organic compounds to two or more types. This was particularly applied by August Kekule. It was also in the fifth decade that Hermann Kolbe, 1818 to 1884, revived the much ridiculed copulae. He and Sir Edward Frankland, 1825 to 1899, were followers of Berzelius and held similar views to Gerhardt. But as they did not accept at that time either the new atomic weights or the existence of radicals containing oxygen, they made use of other formulae. Kolbe united the conclusions deduced from his researches with the declining theory of Berzelius. He induced the latter with new life by casting aside whatever of it was dead and replacing this by vigorous principles. From his own and other investigations, he came to the conclusion that the unalterability of radicals, as taught by Berzelius, could no longer be maintained, since the facts of substitution had to be taken into account. He did indeed adopt Berzelius's hypothesis of copulae, but attached another meaning to these, since he allowed that they exercised a not inconsiderable influence upon the compounds with which they were copulated. He endeavored to make this theory have a deeper bearing upon the constitution of organic compounds, and as a result of the influence of several important researches, his ideas regarding copulae and conjugated compounds were altered several times. His theoretical views, and with them the revived radical theory, reached their completed form in a contribution published in 1859. The principal result of Kolbe's speculations is given as follows. Organic compounds are all derivatives of inorganic, or result from the latter, in some cases directly, by wonderfully simple substitution processes. This idea runs through the 1859 contribution and is illustrated by numerous examples from the wide field of organic chemistry. End of Chapter 12. Section 16.
Section 17 of The Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in June 2017. The Science History of the Universe, Volume 4, edited by Francis Rolt-Wheeler. Chemistry. Chapter 13. Valence, the constitution of organic compounds, and the development of stereochemistry. In the preceding chapter, mention has been made of the influence exerted by Frankland on the views developed by Kolbe respecting the constitution of organic compounds. It was Frankland who, in his now classical paper, A New Series of Organic Compounds Containing Metals, demonstrated that the pairing of the radicals with the elements was to be explained on the ground of some characteristic property of the atoms, and thus he expelled the useless part of the radical theory. 1852. Frankland observed that, quote, when the formulae of inorganic chemical compounds are considered, even a superficial observer is struck with the general symmetry of their constitution. The compounds of nitrogen, phosphorus, antimony, and arsenic especially exhibit the tendency of these elements to form compounds containing 3 or 5 equivalents of other elements, and it is in these proportions that their affinities are best satisfied. Thus, in the ternal group we have NO3, NH3, Ni3, NS3, PO3, PH3, PCl3, SbO3, SbH3, SbCl3, ASO3, ASH3, ASCl3, etc., and in the 5-atom group NO5, NH4O, NH4I, PO5, PH4I, etc. Without offering any hypothesis regarding the cause of this symmetrical grouping of atoms, it is sufficiently evident from the examples just given that such a tendency or law prevails, and that, no matter what the character of the uniting atoms may be, the combining power of the attracting element, if I may be allowed the term, is always satisfied by the same number of these atoms." End quote. He then proceeded to represent the organometallic compounds obtained by formulae which brought out the analogy with the inorganic types from which they were thought to have been derived. From his work on the organometallic compounds, Franklin developed the doctrine of the valence of the elements, the germ of which may be recognized in much that has gone before, particularly in the law of multiple proportions, which stated that the elements show different yet definite stages in their combinations. The so-called doctrine of the polybasic acids contributed materially to the development of ideas upon the subject of the saturation capacity of the atoms. Gay-Lussac, Gmelin, and others inclined to the assumption that the atoms of the various metallic oxides contained one atom of oxygen united to one atom of metal, and that these oxides combined with one atom of acid to form neutral salts. Berzelius also, after 1628, considered that this combining proportion was the rule. However, by Thomas Graham's famous investigation of the phosphoric acids, 1833, it was shown that a view so simple as this, according to which almost every acid was looked upon as monobasic, was untenable. Graham proved that in the ortho-, pyro-, and metaphosphoric acids, for each atom of phosphorus pentoxide, there were 3, 2, and 1 atoms of basic water, these latter being replaced by equivalent amounts of metallic oxides. The saturation capacities of these acids were in this way shown to be dependent upon the amounts of basic water which entered into their constitution. Liebig extended this to many other acids and distinguished between mono-, di-, and tribasic acids, and the property was referred to as the basicity of the atoms, a term which, with the ideas inherent in it, clung for some time to the theory of valence. In 1857, for example, the terms basicity, valency, and atomicity were used as synonymous, and as the measure of the number of hydrogen atoms that could be replaced or held in combination. The idea of basicity was soon extended to the compound organic radicals. In 1855, C. A. Wurtz, 1870 to 1884, a pupil of Liebig and Dumas, showed that glycerin, C3H8O3, may be regarded as the hydrate of the radical C3H5. 4 years previous, A. W. Williamson, 1824 to 1904, had expressed the view that a large number of compounds may be referred to the type of water, the monobasic acids to one molecule, and the polybasic acids, which are of greater molecular complexity, to a condensed water type. He wrote, C2H3O, HO, equals acetic acid. SO2H2O2 equals sulfuric acid. Wurtz now showed that the composition of glycerin could be represented by the formula C3H5 H3O3, which was similar to the formula by which, in accordance with the ideas of Williamson, ordinary phosphoric acid, PO3', H3O3, was represented. Gerhardt, in his Traité de chimie organique, stated that, quote, "In order to compare the radicals among themselves, I propose to refer them all to the radical of hydrogen, and consequently I name them monatomic, diatomic, triatomic, according to the quantity of hydrogen which they are capable of replacing in the type H2O, that is, according to whether they are equivalent to 1, 2, or 3 atoms of hydrogen. So, for instance, in alcohol and in ether, O, C2H5, OH, C2H5, O, C2H5. C2H5, the radical ethyl, is monatomic because it replaces H, one atom of hydrogen, in the type water. End quote. The terms monatomic and polyatomic had been employed much earlier, but in a different sense. Thus, in 1827, Berzelius called fluorine, chlorine, etc. polyatomic, because several atoms of these halogens unite with a single atom of another element. In 1833, Gaudin de Saintes used the same terms to express the number of atoms in a molecule, in which sense they were used by Gmelin, Clausius, and Odling. Williamson attached the idea of capacity for saturation or atomicity of the radical to the number of hydrogen atoms capable of substitution, and the notion of atomicity was soon extended to the known compound radicals and played an important part in the theory of types, etc., which obtained in organic chemistry. Franklin's speculations concerning the substitution value of radicals compared with that of elementary atoms were of great importance, yet they did not meet with immediate approval. By 1858, however, the valence theory had made rapid progress. In this year, Auguste Kekulé first deduced the valence of carbon from its simplest compounds, declaring it to be tetravalent. This had already been recognized by Kolbe and Franklin, if not expressly stated by them. But Kekulé rendered further and much greater service by inquiring into the manner in which 2 or more of these tetravalent carbons were united with one another. The doctrine of atomic chains, open and closed, sprang from this, and the domination of the structural idea in chemistry became complete. In the same year, and independently of Kekulé, M.S. Couper arrived at conclusions almost identical with those of Kekulé. Both Kekulé and Couper expressed with absolute definiteness the axiom that the atomicity of the elements was to be made use of for arriving at the constitution of chemical compounds. The idea of the term atomicity had without any doubt been introduced by Franklin 6 years previous to this. The further development of the above axiom and its utilization in the theory of the linking of atoms was carried out mainly by Kekulé, and in the succeeding years also by Butlerow and Erlenmeyer. While the radical and type theories were attempts at securing an idea of the structure of chemical compounds, it was the valence theory which rendered it possible to furnish a lucid answer to the question as to the composition of such bodies, and, especially after the year 1870, the determination of the constitution of complex molecules became the higher aim of chemistry. Some rudiments of systematic classification had before this been introduced into organic chemistry, and these classificatory beginnings were of great assistance in the erection of structural chemistry. In 1836, Laurent, when he brought forward his nucleus series, arranged organic compounds in series, and it was in 1841 that Gerhardt entered on a research to discover some general law which might suggest an all-sufficing system of classification, and the following year he was ready with his ladder of combustion, with its highest rung cerebral matter, its lowest carbonic acid, water, and ammonia, to enfold the whole science of organic chemistry. He soon found, however, that this arrangement, according to mere complexity of composition, was no sufficient classification, so he betook himself to another line of inquiry. A note of triumph seems to ring through the following lines from the preface to his Précis de chimique organique, published in 1844. Quote, I have succeeded in establishing homologous series. These have indicated to me the means of classifying organic substances in natural families, and of disposing them on a kind of combustion ladder." End quote. As a matter of fact, it was only the word homology that Gerhardt could claim as his own. 2 years earlier, J. Scheele had shown that a very simple relation existed between the alcohols then known, that their radicals might all be represented by the general expression Nr plus H, R suggesting the group C2H2, C = 6. Moreover, in the same year Dumas had demonstrated the existence of a similar relation between the several members of the fatty acids known to him. Yet Gerhardt generalized from this fact of homology, and proved the possibility of predicting the existence of terms unknown in his series. Many systems of classification were suggested during the 6th decade, the classification by series as that of Scheele and Dumas, that of series depending upon formulae, series depending upon chemical behavior, and many other systems. The lack of agreement among chemists, however, as to the formulae belonging to the different compounds, as to the relative weights of the molecules, the atomic weights, and even the number of atoms, prevented a general acceptance of any of the classifications proposed until Kekule established the fact of the tetravalence of the carbon atom, showed the difference between saturated and unsaturated compounds, and deduced his chain formulae. About 1860, Frankland's views regarding a saturation capacity peculiar to the elements were accepted either dilettantly or expressly by most chemists, but it was considered that this saturation capacity, under certain circumstances, might be a varying one. In 1856, Gerhardt had stated that nitrogen was sometimes triatomic and sometimes pentatomic. This view was also held by Frankland, Wurtz, Williamson, and Couper, and the latter three considered that the valence was also variable in the cases of many other elements. Kolbe thought that it must be assumed that a constant valency was characteristic of a few elements, and a varying one characteristic of many more, since he perceived in it another expression for the law of multiple proportions, and nothing was known concerning the cause of valence. As early as 1854, Kolbe had concluded that each element possessed a maximum saturation capacity, but that lower stages of saturation might exist along with this, and toward the beginning of the 60s, several chemists who took an active part in developing the structure theory expressed the same opinion in a more definite manner. Erlenmeyer, in particular, maintained in various papers, and afterward in his Lehrbuch der organischen Chemie, that each element possesses a maximum valency, or that each is furnished with a definite number of affinivalenten, or affinity points, Affinitätspunkten, only part of these, however, being in many cases combined with the affinity points of other elements. Kekule's theory of the constant valence of the elements could not withstand the critical examinations to which it was subjected, however, and in the course of the last 40 years the majority of chemists have adopted the view that the atoms of most of the elements possess a varying saturation capacity, varying according to the conditions. Although the structure theory was unable to accomplish the extreme expectations which aimed at a knowledge of the special arrangement of the atoms, it possessed nonetheless great practical value. The development of organic chemistry since the middle of the 6th decade shows in fact that, through the aid of the structural hypothesis, the discovery of new modes of formation and decomposition of compounds, the recognition of the relations existing between various classes of bodies, and, especially, the interpretation of the constitution of numerous organic substances became possible. Kekule's theory of the aromatic compounds forms the most striking proof of this. In 1865 to 1866, taking the quadrivalence of carbon as his principle, Kekulé called attention to the fact that in the fatty compounds the carbon atoms are linked together by one valence of each. In the case of benzene, the next simplest assumption was made, in accordance with which the carbon atoms are linked together by 1 and 2 valencies alternately, so as to form a closed chain or ring. Of the 24 affinities of the 6 carbon atoms, 18 are employed in linking carbon to carbon. Thus, 6/2 times 4 plus 6/2 times 2 equals 18. 6 valencies then remain which are satisfied by the 6 hydrogen atoms of the benzene. Hence, according to Kekulé, benzene may be represented by means of a regular hexagon whose sides are composed of single and of double lines alternately, the CH groups occupying the corners, thus. Kekulé and his pupils, together with many other chemists who had busied themselves with the derivatives of benzene after this view had been published, now directed their efforts to comparing all the known and rapidly increasing observations bearing upon this class of bodies with the deductions drawn from the above formula, and therewith to proving by actual experiment the admissibility of the assumptions on which the formula was based. The result was that Kekulé's anticipations were realized and his hypothesis substantiated. In 1866, Kekulé had stated that, quote, "What is wanted is that the largest possible number of substitution products of benzene should be prepared by the most diverse methods, that they should be most carefully compared with regard to isomerism, that the modifications so found should be counted." End quote. And in the 1867 edition of his textbook, he called attention to a number of cases of isomerism which at that time had received no explanation. Among these we find that of ethylene chloride with ethylidene chloride, of acetal with diethyl glycol, for maleic and fumaric, for mucic and saccharic acids. The last effort of his philosophy had only found him the two formula C4H2O2H2O2 and C6H8O6H2O2, respectively. Kekulé instanced, too, those bodies which only differed in their effect on polarized light, the tartaric, the malic, and camphoric acids, and the amyl alcohols. It was owing to these cases of isomerism that structural formulae could not be assigned. In some cases a greater number of isomeric bodies were known than could possibly be accounted for by any arrangement of the atoms in formulae upon a plane surface, retaining, of course, the accepted views as to valence, etc., and since these isomers differed principally in certain physical properties, they were at first termed physical isomers. The study of these resulted in the consideration of the arrangement of atoms in space, the chemistry of space, or stereochemistry, in which branch of the science an extended view of atomic grouping was essayed. Modern stereochemistry was anticipated by Emanuel Swedenborg in 1721, when he made an attempt to explain the phenomena of chemistry and physics on geometrical principles in his Prodromus Principorium Rerum Naturalium sive Novorum Tentaminum Chemiam et Physicam Experimentalem Geometricae Explicandi, and similar beginnings were made by Johann Barcusen 10 years earlier. In 1864, Carius, who first used the term physical isomerism, explained it as follows. Quote, "I have tentatively expressed a view as to the cause of what I call physical isomerism. Substances which exhibit this property yield, under the same or nearly the same conditions, products which are either identical or physically isomeric. According to our present views, I think it improbable that such substances should have their atoms differently arranged, that is, that they should be metameric. but it is quite conceivable that in the formation of physical isomers, differences of condition may cause the production of substances with the same arrangement of the atoms within the molecule, but with a different aggregation of these molecules, and that thereon depends the difference in their properties. Thus, we must consider as certainly only physically isomeric a large number of the substances distinguished by the difference of their action on polarized light, such as the two modifications of amyl alcohol, the tartaric acids, the malic acids, etc. This explanation was inadequate, and in 1873 Johannes Valence, 1835 to 1902, who succeeded Kolbe as professor of chemistry at Leipzig in 1885, suggested the substitution of the term geometrical isomerism for physical isomerism. He had been engaged in an investigation of the various modifications of lactic acid, and had found that the ethylene lactic acid, or hydrochloric acid, prepared by Beilstein by treating beta-iodopropionic acid with silver oxide, possessed properties different from those of the ethylene lactic acid obtained from ethylene cyanhydrin. This difference was so marked that he thought it might be explained by assigning the two acids different structural formulae. The first was optically inactive, while the second, paralactic acid, was dextrorotary. This one point of difference appeared hardly sufficient to make it necessary to assign to paralactic acid a structural formula other than that of fermentation lactic acid. It seemed much more likely that here, at any rate, were cases of what Carius had called physical, but what Wislicenus now proposed to call geometrical isomerism. He said, quote, "My conclusion for the present is to declare paralactic acid and the fermentation lactic acid as most probably only geometrically isomeric. Their great similarity, even identity in all chemical properties, the ease of transformation on heating of the first into the second, and their differences, particularly in optical behavior, may all alike be explained on this basis. Concerning the special how of this explanation, I am engaged in experimental investigations." End quote. The next year, J.A. Van't Hoff furnished an answer to this. However, before giving his exposition, mention must be made of Louis Pasteur's (1822 to 1895) pioneer work in this field. Pasteur studied the various tartrates crystallographically and showed that there are 4 isomeric tartaric acids, that is, racemic acid, inactive tartaric acid, and right and left rotating tartaric acids. He showed, moreover, that the two latter acids crystallize in similar, but in oppositely built up, enantiomorph forms, that they both rotate a ray of polarized light through equal angles, but in opposite senses, and that when mixed in equal quantities, they yield optically inactive racemic acid. Further, he succeeded in decomposing racemic acid again into the two optically active tartaric acids by 3 different methods. Pasteur established the correlation of molecular dissymmetry and rotary power in these investigations, and it remained to discover under which conditions the dissymmetry could obtain in 2 molecules structurally identical. This was undertaken in 1874 by J.A. Van't Hoff in Holland and J.A. Lebel in France, who in papers published that year offered an explanation practically the same for cases of isomerism which could not be included under the theories of the time. Van't Hoff states that in general Lebel's original paper and his were in accord, but that while Pasteur's researches formed Lebel's starting point, he took for his own Kekullé's laws of the tetravalence of carbon, to which he added the hypothesis that the 4 valencies are directed toward the corners of the tetrahedron in the center of which is the carbon atom. To quote from Freund's Study of Chemical Composition, quote, Van't Hoff introduced no fundamental change in or addition to the original valency hypothesis. A two-dimensional representation of molecular structure could not at any time have been considered as really true to the actual occurrence, but it was legitimate to use it, because of its greater simplicity, as long as it proved adequate to the purpose. And with this recognition and restriction, we continue to use plain structural formulae in the majority of cases." End quote. Van't Hoff, following up the suggestion that may be found implied in Pasteur's paper, and that was explicitly stated by Wislicenus, introduces into the science the consideration of the arrangement of atoms in space. Quote, "Stereochemistry, from stereos, solid, in the restricted sense of the word, comprises chemical phenomena which demand a consideration of the grouping of atoms in space." End quote. Carbon compounds only were considered at first, but the scope of the phenomena dealt with has been extended and now includes compounds of trivalent and pentavalent nitrogen, of tin, and of sulfur. Van't Hoff's theory of the asymmetric carbon atom, however, met with difficulties on its enunciation. To quote from F. P. Armitage's History of Chemistry, quote, "When Van't Hoff enunciated his theory of the asymmetric carbon atom, he was able to say, with much show of truth, that all optically active substances did contain certainly one such atom. Soon, however, were heard dissentient voices. 'What of propyl alcohol?' asked one, and of styrolene?" demanded another. "The propyl alcohol owes its activity to traces of amyl alcohol," answered Henninger. "The styrolene is impure," said Van't Hoff, and their evidence was irrefutable. But Van't Hoff could not, in 1874, maintain that the presence of one asymmetric carbon atom necessarily implied optical activity, for secondary amyl alcohol and its derivatives, also propylene alcohol, were certainly inactive, yet all contained an asymmetric carbon atom. The problem set the stereochemists was somewhat similar to that of the relation between tartaric and racemic acid, so happily solved years before by Pasteur. His methods were recalled, and Lebel soon showed that these inactive bodies were in reality mixtures of two optically opposite isomers, and, others helping, that indeed every substance with but one asymmetric carbon atom was equally capable of mesotomism. The four varieties of tartaric acid had offered no difficulty. With two asymmetric carbon atoms similarly habited, there was necessarily neutralization or duplication of optical activity. But where two or more carbon atoms occurred, asymmetric by union with different radicals, as in the sugars and their derivatives, many more cases of physical isomerism suggested themselves and have since been verified. Without doubt, the asymmetric carbon atom has made a triumphant progress, winning for Lebel the Jecker Prize of 1881, for Van't Hoff a dominant voice in the scientific councils of the world. It will rank with the phlogiston of Stahl, the oxygen of Lavoisier, the atom of Dalton, and the dualism of Berzelius." End quote. Among the most noted workers in the field of stereochemistry have been A. von Baeyer, Wallach, Victor Meyer, Rieke, Bischoff, Werner, Hantzsch, Auwers, and Overton. Even now the subject is in its infancy, and stereochemical theories are as yet insufficiently advanced to present a clear view of the question of geometrical isomerism. Yet, as Ladenburg has said, quote, "It is beyond doubt that the founding and development of stereochemistry, a name which originated with Victor Meyer, is the most important thing that was accomplished in organic chemistry during the last 2 decades of the 19th century. Stereochemistry possesses a significance for this period similar to that which the foundation and introduction of the theory of aromatic compounds possessed for the 20 years preceding." End quote. End of section 17.
Section 18 of the Science, History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 4, edited by Francis Rolt-Wheeler. Chemistry, Chapter 14, Modern Inorganic Chemistry. Progress in inorganic chemistry during the modern period. A rapid growth in inorganic chemistry ensued after the introduction of the new chemistry by Lavoisier. A mass of information concerning the nature of the elements and their compounds was accumulated, and many new bodies were discovered. However, even now, after the accurate study of the chemical behavior of mineral substances by many careful investigators, we are still far from a definite knowledge of the nature of all the elements and their compounds, and new bodies are from time to time added to the extensive series already known. In the case of the elements, for example, Lavoisier in his Traité de Chimie mentioned 26, while 81 are at the present time accepted. An endeavor to sketch the important advantages in inorganic chemistry since the time of Davy and Gay-Lussac will be made in this chapter. Cadmium was discovered by Strohmeyer in 1817 and about the same time by Hermann. It was named by Strohmeyer cadmia fornicum, or furnace zinc, because it was found in the zinc furnace, cadmia being the original name for zinc. In the same year, lithium was discovered by Arfvedson in petalite and spodumene. The metal was first obtained by Bunsen and Matthiessen in 1855. The name is Greek and means stony, and the metal was so called because it was then supposed to be found only in rocks and not in the plant and animal bodies. Silicon was first isolated in 1810 by Berzelius by fusing together iron, carbon, and quartz, and Wheeler showed that it exists in the crystalline form as well as in the amorphous state. In 1827, Wheeler isolated aluminum by the action of potassium upon its chloride, and 18 years later, St. Clair Deville prepared the metal on a large scale by using sodium, while Bunsen effected its preparation by electrolytic means. Aluminum is now prepared in quantity by the electrolytic decomposition of the oxide alumina dissolved in cryolite. Beryllium or glucinum was also obtained by Wheeler, who effected its isolation in 1828 by the action of potassium upon the chloride. Bromine was isolated by Ballard in 1826 from the mother liquor of sea salt, and was further investigated 3 years later by Lowig, along with iodine, which was discovered by Courtois in 1811 in the ashes of sea plants, and chlorine. It constituted the group of halogen elements of Berzelius, since fluorine was then unknown. The latter was first isolated in 1886 by Moissault by the electrolysis of hydrogen fluoride in the presence of potassium fluoride. Tellurium, which had been discovered by Müller von Reichenstein in 1782, was thoroughly investigated by Berzelius, who discovered an element chemically analogous to it, selenium, in 1817. The isolation of the metals comprising the cerium and yttrium groups has presented numerous difficulties. Although the discovery of yttria, impure it is true, from admixture with other earths, was accomplished by Gadolin in 1794, and investigators have busied themselves with the question, the chemistry of the cerium metals is not even yet completely elucidated and may possibly remain unsolved for a considerable time to come. After Klaproth and Berzelius had independently prepared cerium sesquioxide from cerite, and the latter had identified this as the oxide of a metal, Mosander discovered 2 new oxides in crude yttria, the metals of which, lanthanum 1834 and didymium 1841, he isolated. 2 years later, 1843, he added to these 2 others, erbium and terbium, whose existence and nature is not yet, however, definitely settled, in spite of the admirable work which has been done on the subject. This has given us a better knowledge of yttrium, while yttria, which was formerly held to be a homogeneous substance, has proved itself a mixture of the oxides of various metals, of which, however, Only one or two has yet been isolated. For example, the discovery of scandium by Nilsson and Cleve in 1879, and ytterbium by Mariac. The most recent additions to the knowledge of chemistry of this group of elements and their compounds have been made by Welsbach, Drossbach, Kruse, Winkler, Crookes, Bronner, Baskerville, Urbain, and others. Welsbach separated didymium into preseo and neodymium. An analytical method has been elaborated for the separation of the various constituents of cerium, ytterbium, and thorium earths, which has been of help in the manufacture of mantles for incandescent light burners. Quite recently, Urbain has separated ytterbium into two other elements, neoytterbium and lutetium. In spectrum analysis, chemistry now possesses an exceedingly valuable instrument for investigating rare metals and earths, and its use in the last 5 decades has been extensive. Spectrum analysis has grown out of some apparently insignificant and disconnected observations made by Marggraf, Scheele, Herschel, and others upon the light emitted by flames colored by certain salts. The spectra of such flames were investigated by various scientists, among whom Talbot, Miller, Alter, and Swan deserve first mention, but it was only after Kirchhoff in 1860 proved the definite statement that every glowing vapor emits rays of the same degree of refrangibility that it absorbs, that spectrum analysis became developed by Bunsen and himself into one of the great branches of our science. Its importance for analytical chemistry, especially in the discovery of new elements, is almost beyond mention, and it opened up a new era in chemistry. Roscoe once said, "The spectroscope, next to the balance, is the most useful and important instrument which the chemist possesses." Crookes has remarked, "If I name the spectroscope as the most important scientific invention of the latter half of this century, I shall not fear to be accused of exaggeration." The very importance of the subject prevents an entrance into any long discussion of it here. It has come to form a distinct branch of chemical science. In the hands of men like Bunsen and Crookes, it has explored the recesses of the rocks for minute traces of hidden treasures, while with it, workers like Miller, Huggins, and Lockyer have fathomed the abysses of space and determined the constitution of the stars. Among the elements discovered by the use of the spectroscope were rubidium and caesium in lepidolite, and in the Durkheim mineral water by Bunsen and Kirchhoff, indium by Reich and Richter in 1863 as a constituent of Freiberg zinc blende, gallium in 1875 by Lecoq de Bois-Badron, and thallium by Crookes in 1861. The chemical nature of the last mentioned metal was established by Lamy in the same year. The knowledge of the metals discovered in the preceding era was greatly enlarged by investigations conducted during this period. The analogues of nitrogen, phosphorus, arsenic, antimony, and bismuth were carefully examined, and the atomic weight which Berzelius determined for phosphorus was confirmed by Dumas, while his atomic weight for arsenic was corroborated by Pellouz and Dumas. The metals of the alkaline earths, barium, strontium, calcium, and magnesium, which were isolated by Davy, were investigated by Berzelius, Mariac, and Dumas, who determined their atomic weights. Recently, Winkler found that magnesium is an excellent reducing agent for metallic oxides. Cobalt and nickel have been the subject of researches of an important nature, mainly because of the remarkable compounds they form, for example, nickel tetracarbonyl and the ammonio-cobalic compounds. Nickel is now extensively used in metallurgy, especially in the production of nickel steel. The rarer metals have, of course, received considerable attention. Uranium, which was discovered by Klaproth in 1798, was investigated further by Pelago, Roscoe, and lately by Zimmermann. Molybdenum and tungsten, isolated respectively by Helm and Del Hurriar, have become better known, and the acids and the complicated salts of these have been studied by Scribler, Mariac, Friedheim, and Gibbs. Uranium, and particularly tungsten and molybdenum, are now employed extensively as steel hardening materials. Uranium compounds are also used in dyeing and ceramics. Titanium, zirconium, and thorium have now become, in the form of various compounds, particularly the oxide, of practical importance. Thorium was discovered by Berzelius in 1828. Its oxide, thoria, is applied in the manufacture of Welsbach gas mantles, which consists essentially of a web of 99% thoria and 1% cerium oxide. Titanium is employed for the manufacture of special alloys, and zirconium, as zirconia, is made use of both in gas and electric illumination. Germanium, an element which resembles these in some respects, was discovered by Winkler in 1886 in a Freiberg silver ore. The element vanadium, which was discovered by Del Rio in 1801, was isolated by Roscoe in 1867. He also investigated its compounds carefully, determining its different stages of combination with oxygen and chlorine. This metal, which is widely distributed, is utilized in the production of sheet and tool steel and armor plates. Tantalum, a related metal, which along with columbium or niobium was examined exhaustively by Blomstrand and Mariac, is used in alloys to make small springs and anvils, and in the metallic form to make special incandescent electric light filaments. The metals of the platinum group, platinum, palladium, Woolston in 1803, rhodium, Woolston in 1804, iridium, Tennant in 1803, osmium, Tennant in 1803, and ruthenium, Claus in 1844, have been given careful consideration by chemists. Platinum is used extensively in making chemical apparatus, especially crucibles and stills, and osmium and iridium have recently come into use as filaments for incandescent lamps. About 15 years ago, the number of the chemical elements was enlarged by two gases of great theoretical interest, argon and helium. As early as 1785, Cavendish had noticed that a residue of about 0.6% remained when the nitrogen and oxygen were removed from air, and in 1894 Rayleigh discovered that nitrogen from the atmosphere was 0.5% heavier than nitrogen prepared chemically. Rayleigh and Ramsay then prepared large quantities of this atmospheric residue and found it to be a gas different from nitrogen. They called it argon, from the Greek argos, for lazy. Helium was discovered by Ramsay in 1895 in the mineral cleveite. It had already been found to exist in the chromosphere of the sun by Janssen in 1868, and his observations were confirmed by Franklin and Lockyer. Helium, primarily obtained by heating cleveite with sulfuric acid, and since found in small quantity, often together with argon, found in the minerals uraninite, malacone, etc., as well as in the gases from some mineral water springs, is like argon, inert and indifferent. Up to now, in spite of persistent effort, no compound of either argon or helium has been prepared. And further, although many diffusion experiments with both gases have been carried out, with the object of seeing whether they were really elementary, the densities of both have remained unaltered. For example, it has been found impossible to subdivide them by diffusion into two or more components. From the ratio of the specific heats at constant volume and constant pressure, it follows that the molecule and atom are identical in both argon and helium. For example, that the gases are monatomic, and this applies also to the more recently discovered gases of the air, krypton, neon, and xenon. These were separated from liquid air in 1898 by Ramsay and Travers. The atomic weights of these gases and the proportions in which they are present in the air are as follows. Helium, atomic weight 4, 1 part by volume in air, 2,450 volumes. Neon, atomic weight 20, 1 part by volume in air, 808 volumes. Argon, atomic weight 39.9, 1 part by volume in air, 105 volumes. Krypton, atomic weight 81.8, 1 part by volume in air, 746,000 volumes. Xenon, atomic weight 128, 1 part by volume in air, 3,846,000 volumes. Since the interest attached to these gases has been recently augmented by the discovery of Ramsay and Soddy that radium emanation eventually changes, at least in part, into helium, and since Ramsay has shown that when the radium emanation decays in the presence of water, neon is produced, and that argon results when the decay takes place in the presence of water containing a copper salt in solution, the radioactive elements may be conveniently referred to here. Henri Becquerel found in 1896 that compounds of uranium spontaneously and continuously emit some radiation, which, among other properties, has that of making air a conductor of electricity. This effect, the quantity of which can be determined with great accuracy, was used by Madame Sklodowska-Curie to measure the amount of radiation produced by various compounds of uranium and of thorium, which latter had been found by Schmidt to emit the same kind of radiation. She subsequently tested a large number of rocks and minerals, and found that certain minerals which contain uranium and thorium, for example, pitchblende, oxide of uranium, chalcolite, double phosphate of copper and uranium, possess radioactivity much greater than that theoretically due to the amount of uranium present. Madame Curie therefore inferred that it appeared probable that if pitchblende, chalcolite, etc., possess so great a degree of activity, these substances contain a small quantity of a strongly radioactive body differing from uranium and thorium and the simple bodies actually known. I thought that if this were indeed the case, I might hope to extract this substance from the ore by the ordinary methods of chemical analysis. The investigation was consequently pursued, and with the assistance of her husband, Pierre Curie, and Gustave Beaumont, Madame Curie commenced the laborious treatment of the residue remaining after the extraction of the uranium from pitchblende, a large quantity of which had been placed at her disposal by the Austrian government, and finally separated the salts of radium in 1898. While endeavoring to isolate radium, Madame Curie discovered polonium, and other investigators, de Biernet, Gazelle, Markwald, and Hoffmann, have given the names of actinium, emanium, radiotellurium, and radio-lead to similar substances, the two last being possible products of the spontaneous change in radium. Among those who have worked with success upon the problem of radioactivity, Elster and Gettel, Rutherford, Soddy, and Ramsay may be mentioned here. Radium maintains a temperature 1 or more degrees above that of the atmosphere, injures the eyes, and disorganizes the flesh when kept long in contact with it. Its peculiar properties have been explained in various ways. The most plausible suggestion is that atoms of high atomic weight slowly disintegrate into ultimate corpuscles or particles, and that this decomposition is attendant with the development of great energy. The successive disintegration of the radium atom, as exemplified by the disintegration of products, is shown in the following table, which represents, according to Ernst Rutherford, the complete radium series as at present known. Radium, radiation emitted, alpha particles, period 2000 years, range of alpha particles in air at normal pressure 3.5 centimeters. Radium emanation, radiation emitted, alpha particles, period 38 days, range of alpha particles in air at normal pressure 4.3 centimeters. Radium A, radiation emitted, alpha particles, period 3 minutes, range of alpha particles in air at normal pressure 4.8 centimeters. Radium B, radiation emitted, beta particles, period 26 minutes. Radium C, radiation emitted, alpha and beta particles, gamma rays, period 19 minutes. Range of alpha particles in air at normal pressure 7.06 centimeters. Radium D, radiation emitted, unknown, period 40 years. Radium E, radiation emitted, unknown, period 6 days. Radium F, radiation emitted, beta particles, period 4.5 days. Radium G, radiation emitted, alpha particles, period 140 days. Range of alpha particles in air at normal pressure, 3.86 centimeters. It appears that uranium is the source of radium, and Boltwood has recently announced the immediate parent of radium, ionium. Radium represents barium chemically, and according to Madame Curie and Thorpe, it has an atomic weight of 226.5. Several observers have demonstrated that it possesses a characteristic spectrum, and consequently, notwithstanding its disintegration and peculiar conduct, radium is regarded as a chemical element. Owing to an affidation among chemists to recognize a body as a chemical element when, under proper conditions, it possesses a definite atomic weight and exhibits a spectrum containing characteristic and novel lines. In 1823, Mitscherlich discovered the existence of sulfur in two different crystalline varieties, rhombic and oblique, and a third variety, a plastic form, was also known. Frankenheim learned that by heating and cooling, these varieties could, at definite temperatures, be converted into one another, and in describing these phenomena, the term isomerism was employed, to which, however, Berzelius published an objection in 1841. To quote from his Jahresbericht for that year, I feel compelled to call attention to the fact that the word isomerism, which is applied to different substances composed of an equal number of atoms of the same elements, is not compatible with the view as to the cause of the different properties exhibited by the various modifications of sulfur, carbon, silicon, etc. While the term still lends itself to the expression of the relation between ethyl formate and methyl acetate, it is no longer suitable in the case of simple substances which assume different properties, and it might be desirable to substitute for a better chosen term, for example, allotropy or allotropic modifications. In accordance with these views, there can be more than one cause for that which we call isomerism, namely, 1. Allotropy, in which case the difference between the sulfides of iron is due to the fact that they contain different modifications of sulfur. 2. Differences in the relative position of the atoms in the compound, of which the two kinds of ether, ethyl formate and methyl acetate, are so striking a proof. 3. A combination of 1 and 2. Since then the term allotropy has been in constant use, and numerous allotropic phenomena have been observed, particularly among the non-metals. The allotropism of carbon was the first observed example, 1773, and its modifications exhibit marked points of difference, for instance, comparing diamond and graphite. Carbon, diamond, crystallographic system, cubic, optical properties, colorless, transparent, high refractive index, mu equals 2.417. Chemical and physical properties, non-conductor of heat and electricity, not attacked by oxidizing agents, ignition temperature 760 degrees to 875 degrees, specific gravity 3.52, hardness 10. Carbon, graphite, crystallographic system, hexagonal or oblique, optical properties, opaque, chemical and physical properties, good conductor of heat and electricity, oxidized to graphitic acid, ignition temperature 575 degrees and above, specific gravity 2.25, hardness 1. When amorphous carbon, coal, peat, lampblack, etc., and diamond are heated, they pass into the graphitic variety, and graphite is now produced in large amounts by heating carbon to a high temperature, 4,000 degrees Celsius, by an alternating electric current. Henri Moissan, 1852 to 1907, an eminent French chemist, succeeded in preparing synthetic diamonds by dissolving pure sugar charcoal in molten pure iron and suddenly cooling the mass by plunging it into water, and 3 English chemists, Sir F. A. Abel, W. H. Noble, and Sir William Crookes, obtained diamonds by exploding some of the high explosives in steel bombs, the liquid carbon produced crystallizing as it cooled. However, no diamonds have thus far been produced of commercial size or amount. The most peculiar, as well as noteworthy, example of allotropism is afforded by the conversion of oxygen into ozone. Ozone was first noticed by Van Marum in 1785 in electrified air. In 1840, C.F. Schonbein called attention again to this substance, discovering its oxidizing action, and showed that it was produced in the electrolysis of water and in the slow combustion of phosphorus and sulfur. He gave it the name ozone, which means a smell. The investigations of Marillac, de la Rive, Becquerel, Tate, Fremy, Andrews, and Brodie have proved it to be modified oxygen. Its density was determined by Sauret in 1860. The latter, and before him Andrews, proved that the ozone molecule contains 3 atoms of oxygen, while a molecule of the latter is made up of 2 atoms. Ozone is now used in the sterilization of water. Among other allotropic modifications, those of selenium and phosphorus are of interest. Berzelius investigated the allotropes of selenium, and those of phosphorus were studied by Berzelius, Schroeder, Hittorf, and Schenck. Schroeder discovered the red variety in 1845, and Hittorf found that it could be transformed into a metallic modification. Several additional allotropes of sulfur have been discovered in late years, and the fact that many metals can exist in allotropic forms has been clearly demonstrated. For example, colloidal gold, silver, platinum, and mercury. The list of the compounds of the elements was greatly extended from the time of Lavoisier, particularly with the discovery of new acids and the growing knowledge of the different basicity of the various acids. It is important to mention some of the discoveries of moment. In 1818, one of the most interesting of inorganic compounds was discovered by Thenard. He proved that water is not the sole oxide of hydrogen, but that another, peroxide of hydrogen, but which he termed oxygenated water, may be prepared. This compound plays a prominent role in many processes of nature and is now prepared in quantities by treating barium dioxide with sulfuric acid for disinfecting and bleaching purposes. The list of the halogen acids was completed prior to 1820. Gay-Lussac and Ballard studied hydriodic and hydrobromic acids. The former, Davy and Faraday, investigated hydrochloric acid, while Thenard, Gay-Lussac, and Berzelius contributed greatly to an intimate knowledge of hydrofluoric acid. In 1869, Gore and Nicholas continued the investigation of anhydrous hydrofluoric acid, and the latter lost his life through its action. Gore and Fremy established its composition, but, as before mentioned, the element fluorine was not isolated until 1886. The oxygen compounds of chlorine, iodine, and bromine have been given much attention since the commencement of the 19th century. The work of Gay-Lussac on chloric acid, Ballard on hypochlorous acid, Milan on chlorous acid, and Davy and Stadion on chlorine peroxide was exceedingly valuable and led to researches which firmly established the composition of these bodies. The oxygen compounds of iodine received careful attention in the hands of Davy and Magnus, and the latter discovered iodic acid, the principal compound of that halogen. Following Gay-Lussac's discovery of hyposulfurous acid in 1813 and dithionic acid in 1819, little attention was given to the compounds of sulfur and oxygen until the 4th decade, when the thioacids, which contain more sulfur and are more closely related to sulfuric acid, were recognized. More recently, the early known oxides of sulfur, sulfur dioxide and sulfur trioxide, have received several additions in sulfur sesquioxide, sulfur tetroxide, and sulfur heptoxide. Sulfuric acid, the most important of all chemicals, is used in enormous quantities in the industries, and its manufacture has been immensely developed. Over 2 million tons were used in the United States in 1908. The very poisonous compounds of hydrogen, with phosphorus, arsenic, and antimony, phosphine, arsine, and stibine, were given considerable attention during the first and second decades of the modern period. Phosphine, or hydrogen phosphide, discovered in 1783 by Gendebray, and its composition was studied by Davy. Rose continued its investigation at a later date. Arsine was prepared in a pure state by Soubrain. Gellin fell a victim to its toxic action in 1815. Phosphorus and phosphoric acids were known to Lavoisier, but their constitution was not established until a much later period. It was upon the relations which Gay-Lussac, Stromeyer, and Graham found existing between the ortho, pyro, and metaphosphoric acids that Liebig founded his theory of polybasic acids, which marked such an important step forward in chemistry. The important compound, hydroxylamine, which may be regarded as ammonia, in which a hydrogen atom has been replaced by hydroxyl, OH, was discovered by Lawson in 1865. It has led to a knowledge of many remarkable organic compounds. Similarly, the analogous compound, hydrazine, which was first prepared by Curtis in 1887, has entered into the preparation of a series of interesting compounds, for example, the hydrazones and hydrazides. It is an exceedingly powerful reducing agent. Of the simple carbon compounds, the greater number were discovered in the first decade. Carbon disulfide, which was accidentally discovered by Lampadius in 1796, while heating pyrites with coal, was accurately examined by Vauquelin in 1812. It is now prepared in an electric furnace by conducting sulfur vapor over heated carbon, and finds extensive use as a solvent. Carbonyl chloride, or phosphine gas, was discovered by Davy in 1811, and carbon oxysulfide by von Than quite recently. The compounds of carbon with certain metals, carbides, are now of great technical importance. In 1808, Davy discovered potassium carbide, the first described in chemical literature, and in 1862, Wöhler prepared calcium carbide, now one of the most important on account of its use in the generation of acetylene and in the manufacture of calcium cyanamide, a new constituent of fertilizers. Calcium carbide has, since 1894, been prepared by fusing limestone and carbon together in an electric furnace. Before closing this brief resume of some of the advances made in the knowledge of chemical compounds, mention must be made of the metallic peroxides, hydrides, and nitrides. Sodium peroxide, which was discovered by Gay-Lussac, is now used extensively under the name oxone as a bleaching and oxidizing agent, and calcium peroxide, discovered by Gay-Lussac and Thenard, is used in dentistry. The discovery of the hydrides belongs to the present day. Among the most important of these is calcium hydride or hydrolyte, which is used for generating hydrogen. The metallic nitrides, as magnesium, calcium, boron, and lithium nitrides, have only lately been investigated carefully, but may become of great importance. Numerous important chemical and physical facts were learned concerning the gaseous bodies, especially during the second, third, and seventh decades, and the experiments which were conducted with a view of liquefying gases are of the highest import, more particularly with regard to the production of liquid air and its application to researches at low temperatures. The experiments of Davy and Faraday, in which the gases were generated in curved, closed glass tubes and cooled to about -20°C in a freezing mixture, resulted in the liquefaction of all the common gases, with the exception of hydrogen, nitrogen, oxygen, methane, carbonic oxide, and nitric oxide. In 1834, Thilorier liquefied carbon dioxide in considerable quantities and obtained the solid. He was the first to operate on a large scale, and subsequent investigators made use of many of his observations. Between the years 1844 and 1855, Naderer studied the relationship of pressure and volume over wide ranges of pressure, and in 1852 he exposed hydrogen to a pressure of 2,790 atmospheres, but was unable to effect its liquefaction. It was only in 1877 that Raoul Pictet and Louis Cailletet succeeded, almost simultaneously, in liquefying the majority of the so-called permanent gases. Their success was due to a recognition of the fact that reduction of temperature was necessary as well as pressure, but it was not possible by the aid of the methods and appliances which they employed to obtain the liquids in large quantities and to determine their physical constants. This was accomplished by Wroblewski, a chemist in Krakow, and he had Olszewski first obtain quantities of oxygen and nitrogen in the liquid state and describe many of their properties. These two investigators share with Dewar, an English chemist, the honor of having first devised practical methods for the production of liquid air in quantity. And in 1896, C. Linde in Germany and W. Hampson in England constructed technically efficient forms of apparatus for producing liquid air. Liquid air has not as yet, however, found any technical application upon a large scale. Nearly pure oxygen is obtained from it very cheaply, and the attempt has been made to apply it in the manufacture of explosives, but so far liquid air has achieved the most important results in chemical research. In the first place, it must be mentioned that Dewar, by its aid, has succeeded in liquefying hydrogen and in obtaining air, oxygen and hydrogen in the solid state, and that in doing so he has achieved almost everything that can be done in this direction. However, he is at present attempting to reach the so-called absolute zero. The results that have been obtained by means of this agency with respect to the discovery of the noble gases are of greater importance. Since these have been described, it only remains to be stated that Ons, in his cryogenic laboratory in Leyden, has recently announced that he has liquefied helium and that it boils at negative 268.5 degrees Celsius. End of section 18.
Section 19 of The Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in May 2018. The Science History of the Universe, Volume 4, edited by Francis Rolt-Wheeler. Chemistry. Chapter 15. Atomic Weights and Periodic Law. Part 1. In a preceding chapter, an attempt was made to trace the early development of the atomic theory, and later it was shown how this theory became a necessity for the development of organic chemistry. It had fallen into disfavor because of the difficulties encountered by Berzelius and others in distinguishing between atoms and molecules, but much light was thrown upon this and other matters as the chemistry of the compounds of carbon was better understood, and the fact that the dominant doctrine of the new chemistry quietly assumed the truth of Dalton's theory in all its important particulars was reflected upon the older chemistry, so that this great theory became the basis for it all. The old confusion between atoms and equivalents was not entirely done away with until after Frankland's investigations of the organometallic bodies. Yet, in 1846, Laurent had clearly distinguished between atom, molecule, and equivalent, and his definitions are still current. He stated that the atom of M. Gerhardt represents the smallest quantity of a simple body which can exist in a combination. My molecule represents the smallest quantity of a simple body which must be employed to perform a chemical reaction. This definition of a molecule was employed until quite lately in general, but in 1888 Lothar Meyer pointed out that it was insufficient. Gerhardt defined equivalent as follows, quote, "According to our views, the conception of equivalent implies that of similarity of function. It is known that the same element can play the part of one or other of several very different elements, and it may happen that to each of these different functions corresponds a different weight of the first element." End quote. 7 years previously, in 1842, when he had not arrived at a clear distinction between equivalent and atomic weight, Gerhardt had doubled the equivalents of carbonic acid and of water, and in 1843 he followed this up by doubling the values of the symbol weights used by French chemists, H equals 0.5, O equals 8, C equals 6, etc., rendering them thereby identical with Berzelius's atomic weights. The reasons for this change were derived from the study of chemical reactions. He found that the amounts of water, carbonic acid, ammonia, and sulfurous acid evolved in the interactions between the quantities of organic compounds represented by the formulae assigned to them on chemical grounds, were always two, or multiples of two, equivalent weights of H2O, CO2, SO2, when H equals 0.5, O equals 8, C equals 6, S equals 16. Both Gerhardt and Laurent expressed sound views on the selection of atomic weights. They recommended the choice of such of these as were in agreement with the requirements of the law of isomorphism, the law of Avogadro, and the law of heat capacity, and which above everything are chemically adequate. However, apparently the chemical public was not yet ready for the change. In his great textbook on organic chemistry, the publication of which was begun in 1853, Gerhardt retained Gmelin's equivalent weight notation. He is reported to have said in private conversation that unless he had done so, no one would have bought the work. In the introduction to the book, the matter is put more formally. I have even sacrificed my notation, retaining the old formulae the better to show by example how irrational they are, and leaving to time the consummation of a reform which chemists have not yet adopted. Confusion continued to reign for some time longer. The terms equivalent, atomic weight, molecular weight were used and abused in every conceivable sense, sometimes even employed as synonymous. About the middle of the century, 2 units or standard elements were in use for the determination of combining weights. Dalton had suggested hydrogen as unity, and this standard was adopted by Gmelin and many others. Wollaston and Berzelius took oxygen as the standard, Wollaston giving it the value 10 and Berzelius using it as 100. Thomson had given it the value 1. The standard of Berzelius was the accepted one for a long time, but about 1842 a return was made to the standard of Dalton. It was in this year that Dumas, whose atomic weight determinations are classical, redetermined the ratio oxygen to hydrogen from the composition of water, and had ascertained it to be 15.96 to 2, and had expressed his belief that the true value was probably 16 to 2. His number, which in the same year was confirmed by the results of Erdmann and Marchand, was for a long time considered as extremely exact. However, the work of Jean-Servais Stas, 1813 to 1891, soon after furnished numbers for the combining weights of a large number of elements which had all been determined by direct reference to 16 of oxygen, and the accuracy of which was far superior to that of the ratio oxygen to hydrogen. Indirectly he had obtained for hydrogen in terms of oxygen equals 16.00, the value 2.02. Though not attaching special importance to this result, Stas asserted that the composition of water was not known with sufficient accuracy for hydrogen to be a suitable standard, and he expressed himself in favor of 16 of oxygen. Since, however, 16 was then generally accepted as the exact combining weight of oxygen in terms of the hydrogen standard, Stas' recommendation involved no recalculation, that is, no change in practice, only a change in theory desirable from the point of view of future possibilities. The adoption of the oxygen standard advocated would have meant that if a redetermination of the composition of water should lead to a change in the value of the ratio oxygen to hydrogen, the effect of this would only be an alteration of the value used for the combining weight of hydrogen, and not the necessity of a recalculation and a consequent change of all the combining weight values determined directly in terms of oxygen. Stas' suggestion, which it must be admitted was not pressed strongly, did not receive much support. All the work of Stas was monumental in the care taken to secure accuracy. The determinations of atomic weights by him of importance were those of silver, potassium, sodium, lithium, lead, chlorine, bromine, iodine, sulfur, nitrogen, and oxygen. Much of this work was carried out to prove or disprove the correctness of Prout's hypothesis, and Stas concluded as follows: I have arrived at the absolute conviction, the complete certainty, as far as it is possible for a human being to attain to certainty in such a matter, that the law of Prout, together with M. Dumas' modifications, is nothing but an illusion, a mere speculation definitely contradicted by experience. In 1860, J.C. Marignac (1817 to 1894), who had determined the atomic weights of a number of elements, published a paper in support of what he termed Prout's law. He observed that the differences between the result obtained by M. Stas and those required by the law of Prout are certainly very small, but they are considerably greater than the greatest differences between the results obtained in each set of experiments. The results referred to, as well as those of Marignac himself, are appended. Silver, Stas, 1860, 107.943, Marignac, 107.921, Prout, 108. Chlorine, Stas, 35.46, Marignac, 35.456, Prout, 35.5. Potassium, Stas, 39.13, Marignac, 39.115, Prout, 39. Sodium, Stas, 23.05, Prout, 23. Ammonium, Stas, 18.06, Prout, 18. Nitrogen, Stas, 14.041, Marignac, 14.02, Prout, 14. Sulfur, Stas, 16.037, Prout, 16. Lead, synthesis of sulfate, Stas, 103.453, Prout, 103.5. Lead, synthesis of nitrate, Stas, 103.460, Prout, 103.5. Marignac reasoned from Stas's results that Prout's hypothesis was substantiated rather than disproved. He employed the two arguments of the Proutians that Stas's numbers were very close approximations to whole numbers, and hence could be considered as such, and that those approximations were too numerous to be accidental. This fatal error of rounding off fractions into whole numbers was the very thing which misled Prout at the beginning, and with him there was far more excuse for it. Marignac further said that should future determinations of other elements give similar approximations, he would feel assured of the existence of some fundamental cause which brought about the multiple relation of the atomic weights and subordinate causes which modified it. He thought that Prout's law deserved to rank with that of Gay-Lussac or of Mariotte. In another place, Marignac referred to Prout's law as one of those not absolute but only approximate laws, like many other natural laws. From 1888 onward, there appeared in quick succession redeterminations of the ratio oxygen to hydrogen, all demonstrating that Dumas's experimental number 15.96 was too high, but in the meantime Lothar Meyer and Seubert, strong champions of the hydrogen standard, had made this value the basis of very popular atomic weight tables. The new data did not provide a sufficiently reliable number to make recalculations of all the other values desirable, and the obvious way out of the difficulty, the use of the tables of Ostwald, in which the 16.000 oxygen standard was used, was not generally accepted. As a result, two tables of atomic weights, one based on O equals 16 and the other on O equals 15.96, were in use until quite recently. From the year 1896 onward, K. Seubert exerted himself to effect a general agreement with regard to the basis upon which all atomic weights should be founded, and in 1900 an International Atomic Weights Commission was appointed for the purpose of settling the question. The result of their deliberations has been to make oxygen, O equals 16, the official basis instead of hydrogen, H equals 1. The hydrogen unit is, however, often preferred still, both in practical work and in teaching. The main ground for the Commission's taking oxygen as the foundation is the fact, originally brought forward by Berzelius, that by far the greater number of the atomic weights have been derived from compounds of oxygen and not from compounds of hydrogen. Among the chemists other than those mentioned, whose efforts were directed to improving the methods of determining atomic weights, may be mentioned Turner, Penny, Marchand, Pelouse, Deville, and Scherer. Recently, Morley and Richards have done noteworthy work. The most recent table of international atomic weights is as follows. Aluminium, Al, 27.1. Antimony, Sb, 120.2. Argon, A, 39.9. Arsenic, As, 75.0. Barium, Ba, 137.37. Bismuth, Bi, 208.0. Boron, B, 11.0. Bromine, Br, 79.92. Cadmium, Cd, 112.40. Cesium, Cs, 132.81. Calcium, Ca, 40.09. Carbon, C, 12.00. Cerium, Ce, 140.25. Chlorine, Cl, 35.46. Chromium, Cr, 52.1. Cobalt, Co, 58.97. Columbium, Cb, 93.5. Copper, Cu, 63.57. Dysprosium, Dy, 162.5. Erbium, Er, 167.4. Europium, Eu, 152.0. Fluorine, F, 19.0. Gadolinium, Gd, 157.3. Gallium, Ga, 69.9. Germanium, Ge, 72.5. Glucinum, Gl, 9.1. Gold, Au, 107.2. Helium, He, 4.0. Hydrogen, H, 1.008. Indium, In, 114.8. Iodine, I, 126.92. Iridium, Ir, 193.1. Iron, Fe, 55.85. Krypton, Kr, 81.8. Lanthanum, La, 139.0. Lead, Pb, 207.10. Lithium, Li, 7.00. Lutetium, Lu, 174.0. Magnesium, Mg, 24.32. Manganese, Mn, 54.93. Mercury, Hg, 200.0. Molybdenum, Mo, 96.0. Neodymium, Nd, 144.3. Neon, Ne, 20.0. Nickel, Ni, 58.68. Nitrogen, N, 14.01. Osmium, Os, 190.9. Oxygen, O, 16.00. Palladium, Pd, 106.7. Phosphorus, P, 31.0. Platinum, Pt, 195.0. Potassium, K, 39.10. Praseodymium, Pr, 140.6. Radium, Ra, 226.4. Rhodium, Rh, 102.9. Rubidium, Rb, 85.45. Ruthenium, Ru, 101.7. Samarium, Sa, 150.4. Scandium, Sc, 44.1. Selenium, Se, 79.2. Silicon, Si, 28.3. Silver, Ag, 107.88. Sodium, Na, 23.00. Strontium, Sr, 87.62. Sulfur, S, 32.07. Tantalum, Ta, 181.0. Tellurium, Te, 127.5. Terbium, Tb, 159.0. Thallium, Tl, 204.0. Thorium, Th, 232.42. Thulium, Tm, 168.5. Tin, Sn, 119.0. Titanium, Ti, 48.1. Tungsten, W, 184.0. Uranium, U, 238.5. Vanadium, V, 51.2. Xenon, Xe, 128.0. Ytterbium or neoytterbium, Yb, 172.0. Yttrium, Y, 89.0. Zinc, Zn, 65.7. Zirconium, Zr, 90.6. Reverting to the middle of the past century, one finds that much of the credit of removing the difficulties attending the determination of the atomic weights, and of transferring them to a more substantial foundation than had hitherto been in use, is due to Stanislao Cannizzaro, 1826. It was he who, by his criticism in a paper entitled Sunto di un corso de filosofia chimica, Outlines of a Course of Chemical Philosophy, 1858, elucidated the methods employed for arriving at the relative atomic weights of the elements. He recognized, as especially reliable, the deduction of these values from the vapor densities of chemical compounds, a method now in universal use. Cannizaro's paper began as follows. Freund. Quote, "It seems to me that the progress of chemistry within the last year has served to confirm the hypothesis of Avogadro, Ampere, and Dumas concerning the similar constitution of gaseous substances, namely, the assumption that equal volumes of gases, whether elementary or compound, contain an equal number of molecules. But they by no means contain an equal number of atoms, the reason for this being that the molecules of different substances, or even of the same substance in the different states which it can assume, may consist of a different number of atoms of the same or of different kinds. In order to bring my pupils to this same conviction, I have let them follow the same path that had led me to it, namely, that of the historical examination of chemical theories. I begin by showing how, from a consideration of the physical properties of gases, together with Gay-Lussac's laws concerning the relation between the volume of a compound and that of its constituents, there has arisen, as it were, of itself, that hypothesis which was first enunciated by Avogadro and shortly afterward by Ampere. While expounding in detail the line of argument followed by these two physicists, I proceed to prove that it is not in contradiction to a single known fact, provided only that we do as they did. 1. Distinguish between the molecules and the atoms. 2. Avoid confounding the criteria for comparing the weights and numbers of molecules which those employed for ascertaining the weights of atoms. 3. Abandon the erroneous view that while the molecules of a compound may consist of any number of atoms, those of the different elements must consist of one atom only, or at any rate of an identical number of atoms." End quote. He then discussed molecular weight determinations and showed that the hypothesis of Avogadro was a guide in such work. His argument in favor of making the weight of half the hydrogen molecule the standard met with favor and acceptance. Turning from the molecule to the atom, Cannizzaro showed that the law of Dulong and Petit and Avogadro's hypothesis were a guide in the determination of the atomic weights. To quote further from his paper, quote, "We need proceed to the investigation of the composition of the molecules. Whenever the substance cannot be decomposed, it must be assumed that the whole weight of its molecules is composed of one kind of matter only. But if the substance is a compound, we analyze it, and thereby determine the invariable ratio by weight of its constituents, and we then proceed to divide the molecular weight into parts proportional to those of the relative weights of the constituents, and thus obtain the quantities of the elements contained in a molecular weight of a compound, all of them referred to the same unit in terms of which all molecular weights are expressed. According to this method, I compiled a table of molecular composition which follows. Name of the substance: hydrogen. Weight of one volume, or molecular weight, referred to the weight of a half hydrogen molecule equals 1. 2. Weights of the constituents of one volume or of one molecule, all referred to the weight of a half hydrogen molecule equals 1. 2. Hydrogen. Name of the substance: oxygen. Weight of one volume or molecular weight, referred to the weight of a half hydrogen molecule equals 1. 32. Weights of the constituents of one volume or of one molecule, all referred to the weight of a half hydrogen molecule equals 1. 32. Oxygen. Electrified oxygen: 128. 128. Oxygen. Sulfur under 1.000 degree: 192. 192. Sulfur. Sulfur above 1.000 degree: 64. 64. Sulfur. Phosphorus: 124. 124. Phosphorus. Chlorine: 71. 71. Chlorine. Bromine: 160. 160. Bromine. Iodine: 254. 254. Iodine. Nitrogen: 28. 28. Nitrogen. Arsenic: 300. 300. Arsenic. Mercury: 200. 200. Mercury. Hydrochloric acid: 36.5. 35.5 chlorine, 1 hydrogen. Hydrobromic acid: 81. 80 bromine, 1 hydrogen. Hydriodic acid: 128. 127 iodine, 1 hydrogen. Water: 18. 16 oxygen, 2 hydrogen. Ammonia: 17. 14 nitrogen, 3 hydrogen. Arsenine: 78. 75 arsenic, 3 hydrogen. Phosphine: 35. 32 phosphorus, 3 hydrogen. Mercurius chloride: 235.5. 35.5 chlorine. 200 mercury. Mercuric chloride, 271. 71 chlorine, 200 mercury. Arsenic chloride, 181.5. 106.5 chlorine, 75 arsenic. Phosphorus chloride, 138.5. 106.5 chlorine, 32 phosphorus. Ferric chloride, 325. 213 chlorine, 112 iron. Nitrous oxide, 44. 16 oxygen, 28 nitrogen. Nitric oxide, 30. 16 oxygen, 14 nitrogen. Carbonic oxide, 28. 16 oxygen, 12 carbon. Carbonic acid, 44. 32 oxygen, 12 carbon. Ethylene, 28. 4 hydrogen, 24 carbon. Propylene, 42. 6 hydrogen, 36 carbon. Acetic acid, 60. 4 hydrogen, 32 oxygen, 24 carbon. Acetic anhydride, 102. 6 hydrogen, 48 oxygen, 48 carbon. Alcohol, 46. 6 hydrogen, 16 oxygen, 24 carbon. Ether, 74. 10 hydrogen, 16 oxygen, 48 carbon. From this it follows that all the different quantities of hydrogen contained in the molecules of the different substances are whole multiples of the quantity contained in the hydrochloric acid molecule. He defined the atomic weight as the weight of one atom of the element referred to the weight of the hydrogen atom taken, equals 1.00, or oxygen equals 16.00, and stated that it is determined by finding the least amount of the element present in the molecular weight of any of its compounds, which, if these are volatile, is the least amount present in 2 volumes of any of these compounds in the gaseous state. It is unnecessary that the molecular weight of the element be known, only the molecular weights of as many volatile compounds as possible, together with the composition of these compounds expressed as parts of the molecular weights. Chemists were thus taught to rely on Avogadro's hypothesis, all inferences drawn from which, Cannizzaro showed, are in complete agreement with all the physical and chemical laws so far discovered. He gave, as an application of Dulong and Petit's law, the following. The specific heat of copper in the free state confirms the atomistic conception of its chlorides based on analogies with the corresponding chlorides of mercury. Their composition leads us to the inference that they have the formulae CuCl and CuCl2, and that the atomic weight of copper is 63, a fact made apparent by the following relations. Cuprous chloride, ratio between the components expressed by numbers whose sum is 100, chlorine to copper, 36.04 to 63.96. Ratio between the components expressed by the atomic weights, 35.5 to 63 equals Cl to Cu. Cupric chloride, ratio between the components expressed by numbers whose sum is 100, chlorine to copper, 52.98 to 47.02. Ratio between the components expressed by the atomic weights, 71 to 63 equals Cl2 to Cu. But the number 63 for the atomic weight, when multiplied by the specific heat of copper, gives a product nearly equal to that of the atomic weight of mercury or of iodine multiplied by their respective heats. We get atomic weight of copper, 63, times specific heat of copper, 0.09515, equals 6. By the use of this law and Avogadro's hypothesis, an approximation to a correct table of atomic weights was obtained, and the road for the inception of the great natural law underlying them was opened up. Before the atomic theory was formulated, numerical relations were proposed by Richter, the founder of stoichiometry, between the equivalents obtained by him for the various bases and acids. This mathematical work served but little purpose beyond bringing the whole subject of his equivalents into some disrepute. Only a few years passed after the publication of the first tables of atomic weights before their interrelation became a subject of speculation and research. In 1815 we have Prout pointing out the strange fact of their close approximation to whole numbers and boldly rounding them off into such. If they were integral multiples of hydrogen, he reasoned, then this might be the primal matter and all elements made up of it. The Multiplenfieber quickly took possession of the chemical world, even of conservative, level-headed workers such as Berzelius. Enthusiastic support was given it by the English chemists especially, and, when Berzelius afterward became its great antagonist, Thomson and others busied themselves in its defense. The newly organized British Association devoted its fresh energies to an examination into the condition of the various sciences, and, among other inquiries, set on foot one as to the grounds for believing in what was then called, and has been often so called since, Prout's law. The result of this inquiry was adverse to the law, and it would have been dropped, in all probability, had it not been taken up by Marignac, Dumas, and the French chemists, with certain modifications rendered necessary by the more perfect knowledge of the atomic weights. Meanwhile, a different style of numerical regularity had been brought to the notice of chemists. In 1817, Döbereiner first noticed the strange grouping of analogous elements into threes, or triads, as they soon came to be called. He said, according to Venable, noteworthy relations are revealed when one examines the stoichiometrical values of the chemical elements and compounds arranged in series. 1. Those most often found in plants have the smallest values and are the most abundant. The highest values are less widely distributed. 2. Those corresponding in many physical and chemical properties as iron, cobalt, and nickel have almost the same stoichiometrical value. 3. Compounds which have like equivalent numbers are almost alike in chemical constitution. End quote. For a long period following this paper, there was no further attention given to this question, but in 1829 Döbereiner published another paper, which appears to have been a result of the atomic weight determinations of Berzelius in 1825. He indicated that the atomic weight of bromine approximates the arithmetical mean of the atomic weights of chlorine and iodine, namely 35.470 plus 126.470 divided by 2 equals 80.970, considering h equals 1. Of this mean he stated that though somewhat greater than 78.383, the number actually found by Berzelius, it so closely approximates to it as to justify the hope that repeated accurate determinations of all the atomic weights involved will lead to a disappearance of any difference. He found similar relations for the alkaline earths, the alkalis, and for the group comprising sulfur, selenium, and tellurium, as shown by the equations. 356.019 equals calcium plus 956.880 equals barium divided by 2 is equal to 656.449 equals strontium. But experiment gave for strontium, regarding O equals 100, 647.285. 195.310 equals natrium plus 589.916 equals potassium divided by 2 is equal to 392.613 equals lithium, but experiment gave for lithium, regarding O equals 100, 390.897. 32.239 equals sulfur plus 129.243 equals tellurium divided by 2 is equal to 80.741 equals selenium, but experiment gave for selenium, considering H equals 1, 79.263. End of section 19. Section 20 of The Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in May 2018. The Science History of the Universe, Volume 4, edited by Francis Rolt-Wheeler. Chemistry. Chapter 15. Atomic Weights and Periodic Law. Part 2. For more than 20 years, little was added to the work of Döbereiner, and no new ideas were advanced. This was in part due to imperfections in the determinations of the atomic weights, and ignorance as to whether they should be written as had been done by Berzelius, or many of them doubled, as was done by Gerhardt. Further, the whole question of atomic weights was in much doubt, and numerical speculations concerning them would have had little significance during this period. The first to continue the consideration of such triads was Dumas, who in 1851 called attention to the triads of Döbereiner and suggested that in a series of bodies, providing the extremes are known, the intermediate bodies might be discovered, and stated that a suspicion arose as to the possibility of the intermediate body being composed of the extremes of the series, and thus processes of transmutation might be hoped for. The next year, P. Kremers pointed out the existence of certain regularly ascending series among the elements, and in 1858 he followed up the old idea of triads, arranging the elements in the form of conjugated triads, thus lithium equals 7, natrium equals 23, potassium equals 39, magnesium equals 24, zinc equals 40, cadmium equals 112, calcium equals 40, strontium equals 87.5, barium equals 137. In these triads we have the following proportions: lithium to natrium to potassium as 7 to 23 to 39, as lithium to magnesium to calcium. Such close agreement was not found in every case, however, and in 1863 Kremers gave up the doctrine of triads. In 1853 J. H. Gladstone announced that he found the numerical relations between the elements to be of three varieties, namely, 1. The atomic weights of analogous elements are the same. 2. The atomic weights of analogous elements are in multiple proportions. 3. The atomic weights of analogous elements may differ by certain regular increments. He considered the doctrine of triads as partly a natural law. The following year, J. P. Cook published a study of these numerical relations. He stated that the triads broke up natural groups of elements, a fatal blow to the doctrine, and classified the elements into 6 series, in each of which the number whose multiples form the differences is different and may be said to characterize the series. In the first it is 9, in the second 8, in the third 6, in the fourth 5, in the fifth 4, and in the last 3. The elements were further arranged in series according to the strength of their electronegative properties, or, in other words, as their affinities for oxygen, chlorine, sulfur, etc. increased, while those for hydrogen decrease as we descend. Cook laid stress on the fact that his grouping demonstrated that the elements may be classified in a few series similar to the homologous series of organic chemistry. In 1851, John Mercer carried out this comparison with the organic radicals more fully, basing his work partly on that of Max von Pettenkofer, who, while engaged on the subject of the regularities in the atomic weights, made the following comparison. 1. The equivalents of the inorganic elements, which form natural groups, show among themselves such constant differences as the equivalents of organic compound radicals which belong to natural groups. 2. The simple inorganic elements can therefore be regarded from the standpoint of the compound organic radicals. Pettenkofer also criticized the doctrine of triads. Lenssen and Odling were about the last chemists to attempt to develop the doctrine of the triads. The former gave 20 triads, grouping the elements according to their chemical and physical characteristics, but this classification was unsatisfactory, and he suggested a division in dyads, the third member forming a binding member. For example, the triads potassium, natrium, and lithium became dyad potassium, natrium, and binding member lithium. The consideration of the numerical regularities of the atomic weights from the point of view of the homologous organic series, of which the ideas of Pettenkofer form a good illustration, was also taken up by Dumas, who later published his view of double parallelism. He made this comparison. Nitrogen equals 14, phosphorus equals 31, arsenic equals 75, antimony equals 122, fluorine equals 19, chlorine equals 35.5, bromide equals 80, iodine equals 127. On adding 108 to the number for nitrogen, we obtain that for antimony, and on adding it to fluorine, we get iodine, and so the addition of 61 gives us respectively arsenic and bromide. These facts teach the propriety, he says, of arranging the metals in series that shall show a double parallelism, for such a classification brings to view the various analogies existing between these elements. None of these considerations materially advanced the subjects of triads from the state in which it had been left by Döbereiner. But, to quote from Freund's Study of Chemical Composition, when stress had once been laid on the approximate constancy of the differences in the atomic weights of elements forming a group, the ever-dominant desire for simplicity in numerical relations asserts itself. This led to unjustifiable attempts to alter the experimental values in order to make them agree with preconceived ideas. We know how variable and arbitrary were the criteria, prior to 1860, used in the determination of equivalent and atomic weights in general, but in the special cases of groups of elements there was more uniformity, hence the numbers obtained were comparable, and since the above considerations concerning classification applied only to groups of elements, it was possible to bring out within this compass a relation between atomic weight and properties. The extension to the case of elements in general soon followed. This was done in a set of short papers published from 1863 onward by Newlands, the forerunner of Lothar Meyer and Mendeleev. The work of Newlands followed immediately upon that of de Chamcourtois, who was the first to devise a symmetrical arrangement of the elements in his theory of the telluric screw. His first paper, 1863, considered some numerical relations between the atomic weights. To quote from Venable's Periodic Law, these relations were in part along the lines of the old triads. Thus, zinc was pointed out as the mean between magnesium and cadmium, copper between cobalt and zinc. In the group of the alkalis, one of lithium and one of potassium made 2 of sodium, one of lithium and 2 of potassium made 1 of rubidium, etc. Similar relations were observed for other groups. He also endeavored to show a certain kind of symmetry when the lowest member of a group was subtracted from the next higher member, and when the lowest member of a triad was deducted from the highest. In a paper published in 1864, Newlands furnished a table containing the elements arranged in the order of their atomic weights. In a side column the differences between these weights were given, each being deducted from the one next higher in the scale. The next year Newlands announced his law of octaves, which he deduced from his arrangement of the elements. He said in part that if the elements are arranged in the order of their equivalents, with a few slight transpositions, as in the accompanying table, it will be observed that elements belonging to the same group usually appear on the same horizontal line. It will also be seen that the numbers of analogous elements generally differ either by 7 or by some multiple of 7. In other words, members of the same group stand to each other in the same relation as the extremities of one or more octaves in music. The same year he gave as an explanation of the existence of triads the fact that, in conformity with the law of octaves, elements belonging to the same group generally have numbers differing by 7 or by some multiple of 7. That is to say, if we begin with the lowest member of a group, calling it 1, the succeeding members will have the numbers 8, 15, 22, 29, etc., respectively. But 8 is the mean between 1 and 15, 15 is the mean between 8 and 22, etc., and therefore, as an arithmetical result of the law of octaves, the number of an element is often the exact mean of those of 2 others belonging to the same group, and consequently its equivalent also approximates to the mean of their equivalents. 2 years before the presentation of Newland's paper before the London Chemical Society containing the Law of Octaves, Lothar Meyer published the first edition of his Die modernen Theorien der Chemie, in which he gave a table of the elements arranged horizontally according to their atomic weights, so that analogous elements stood under one another, and the change of valence, along with that of atomic weight, could be easily observed. This was Meyer's first attempt, and his table exhibited less evidence of periodicity than that of Newland's, but it caused Meyer to give the question of the relationship of the atomic weights more serious consideration, and his mind continued working on the atomic relationship. His first table had been in the following form. On leaving Eberswald in 1868, he left with his successor the following elaborate table according to Seubert. The following year, Dmitri Mendeleev, 1834 to 1907, a Russian chemist, published his first paper embracing the important principles of the periodic law. He states that he was led to the consideration of the question in this way. When I undertook to write the textbook entitled The Foundations of Chemistry, I had to decide for some one system, lest in the classification of the elements I should have allowed myself to be guided by accidental, and so to speak, instinctive reasons, rather than by an accurate and definite principles. Mendeleev then showed that the principles hitherto used in classification had not been of a quantitative nature, and he laid stress on the superiority of a system which is based on numerical relations, and therefore leaves no scope for arbitrary interpretation. Consideration of the numerical data available in the case of the elements led him to the rejection of the optical, electrical, and magnetic properties, because these vary with the conditions, and of the vapor density, because this is not known for many elements, and is different for the allotropic modifications. He next emphasized the unalterability of the atomic weight, stating that, "For this reason I have tried to take as basis for my system of classification the value of the atomic weight. Beginning with the one of smallest atomic weight, I arranged the elements according to the magnitude of their atomic weights, when it became evident that there exists a kind of periodicity in the properties of the simple substances. Hence, in this system of classification, the atomic weight of an element determines the place to be assigned to it, and all the comparative investigations that I have made lead me to the conclusion that the magnitude of its atomic weight determines the character of an element in the same measure as the molecular weight determines the properties and many of the reactions of a compound. I designate by the name of periodic law the mutual relations between the properties of the elements and their atomic weights, relations which are applicable to all the elements, and which are of the nature of a periodic function." Mendeleev's first table was very imperfect, and the scheme of arrangement he followed was not entirely according to the size of the atomic weights. It was according to this arrangement. He made use of other arrangements also, but the tables which he gave in 1871 contained a plan resorted to in its final and perfected form. One of these tables gave the horizontal and the other the vertical method of arrangement. These follow. These tables contain the periodic law as it is known to us. They have not been very materially altered, though they have been corrected in minor points. The work since has been mainly one of elaboration, and, as Venable observes, the credit for the expansion and filling out of the periodic law, its extension to the other properties of the elements, and the bringing of the various compounds of these elements into consideration also, has been almost entirely due to the skill and knowledge of Mendeleev. In 1870, Meyer offered a full table representing the nature of the elements as a function of their atomic weights, which was so similar to Mendeleev's that many accused him of plagiarism, but his claims to the authorship of the periodic law are based on his 1864 and 1868 tables, and his 1870 system appears to have been an expansion of his earlier tables. It is generally considered that Mendeleev and Meyer worked out the periodic law independently. The periodic law soon attracted merited attention, but for several years its importance was not generally recognized, and it was not until the discovery of some new chemical elements, thereby fulfilling certain predictions of Mendeleev, that it became accepted. Mendeleev had obtained the atomic weights of elements not fully investigated by taking the mean of the weights of what he termed the atom analogues. For instance, the atom analogues of selenium were arsenic and bromine on the one hand, sulfur and tellurium on the other. Its atomic weight should be 75 plus 80 plus 32 plus 125 divided by 4 equal to 78. He also had applied the periodic law to the determination of the properties of unknown elements. This was accomplished by estimating the physical and chemical character from those of the atom analogues, since he had established that all properties were functions of atomic weight. He described the properties of 3 undiscovered elements, and the following values he predicted will show why the periodic law was finally gladly accepted. Eka aluminium, suggested by Mendeleev, atomic weight 68, specific weight 6.0, atomic volume 11.5. Gallium, discovered in 1875 by Lecoq de Boisbaudron, atomic weight 69.9, specific weight 5.96, atomic volume 11.7. Eka boron, suggested by Mendeleev, atomic weight 44, oxide Eka-boron 2O3, specific weight 3.5, sulfate, Eka-boron 2, SO4, 3, double sulfate not isomorphous with alum. Scandium, discovered in 1879 by Nielsen, atomic weight 43.97, oxide scandium 2O3, specific weight 3.864, sulfate scandium 2, SO4, 3, double sulfate 3 kalium 2, SO4, scandium 2, SO4, 3, crystallizes in fine columns. The other, Eka-silicon, ES equals 72, was discovered by Winkler in 1886. It is now called geranium, GE equals 72. At the present time, all chemists recognize the dependence of the properties of the elements upon the atomic weights, and the periodic law has become the central idea in the classification and study of the elements and their compounds. This law is the greatest discovery in chemistry since the announcement of Dalton's atomic theory, and has been much more rapidly accepted. It promises to lead up to results of the utmost importance. The close and mystifying relationship existing between the chemical elements which was revealed by the periodic law naturally has attracted the minds of scientists to thoughts similar to the conception of one primordial matter, as expressed by the Ionian philosophers, and later by Bacon, Descartes, and Boyle. To quote Freund, "Within the last 2 decades, experimental evidence, physical and chemical, has been accumulating in support of these speculations, and the last few years' contributions have been such as to make the complexity of the atoms as much of an established fact as that of the molecular and atomic structure of the masses of matter that we perceive. Moreover, the empirical results which, taken in their entirety, can almost be said to have proved this point, have also supplied evidence which justifies the course hitherto followed by chemists in assigning to the atoms a very special place in the scale of the complexity of different kinds of matter. It seems that the diversity of matter begins only with the atom, that while the component parts of a molecule A are not the same as those of another kind of molecule B or C or D, etc., the constituents of an atom M are identical with those of any other different atom P or Q or R, etc., that all atoms are compounded of the same one kind of primordial matter." The most important papers which have been published on the unity of matter and on the composite character of the elements are those of Sir William Crookes, Anton Grunwald, Gustav Wendt, Henry Wilde, Edward Moisel, W. Pryor, C. T. Blanchard, and Sir Norman Lockyer. Of these speculations and views, the most important is the hypothesis of Crookes. According to him, the chemical elements have resulted by gradual condensation from a primary material which he terms protyle. He arrived at this view in 1886 from observations on the phosphorescent spectra of the yttrium earths. When he advanced this hypothesis provisionally, Crookes had to assume the complexity of the elementary atoms, but since then, experimental and theoretical knowledge on this point has become more definite, as is shown by J. Thomson's investigations on the structure of the atom. Thomson started from the hypothesis that the atom is an aggregation of a number of simpler systems, and that these are formed by corpuscles associated with equal charges of positive electricity. He then traced the analogies between atomic structures and atomic properties, and furnished an explanation for the empirical relations between atomic weight and atomic properties embodied in the periodic law. As Freund remarks, in a section of the community usually referred to as the general public, there seems to be an impression that the recognition of the divisibility of the atom has dealt a death blow to that atomic theory which was founded by Dalton just 100 years ago. No misconception could be more complete. While nothing has had to be given up, nothing to be modified, there has been deepening of the foundations, extension of scope, correlation with other sciences. Except that some of the anticipations expressed have since been realized, the situation today is what it was when Kekule stated that while from a philosophical standpoint he did not believe in the actual existence of atoms, yet as a chemist he regarded the assumption of atoms not only as advisable, but as absolutely necessary in chemistry. End of section 20.
Section 21 of The Science, History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Warren Kati, Gurnee, Illinois. The Science, History of the Universe, Volume 4, edited by Francis Rolt-Wheeler, Chemistry. Chapter 16, The Development of Applied Chemistry. Analytical chemistry, that division of chemistry which treats of the methods of ascertaining the chemical composition of substances and mixtures, both as to kind, qualitative analysis, and quantity, quantitative analysis, has been an indispensable aid to all branches of chemistry, pure and applied, during their modern development, and has itself undergone considerable elaboration and perfection. In particular, analytical methods, both qualitative and quantitative, have been and are being continuously improved. The services of Boyle, Hoffman, Marggraf, Scheele, and Bergman in qualitative analysis have been mentioned, and it will be remembered that Bergman was the first to publish a system of qualitative analysis in the wet way. He laid a firm foundation for the methodical employment of reagents, and the methods of qualitative analysis now in use have been developed from his analytical course of procedure. Wilhelm August Lapidus and Johann Gottling contributed materially to the systematic arrangement of the analytical methods in use during the first decade. The former published in 1801 his Handbuch der chemischen Analyse der Mineralkörper, and the latter his Praktische Anleitung zur prüfenden und zerlegenden Chemie in 1802. Other works followed these, and analytical methods became known and improved. Qualitative analysis in the dry way has been perfected by the use of the blowpipe, an instrument which was originally employed for soldering metals, and which was first employed for testing minerals by Cronstedt and Engström. Bergman and Gahn studied thoroughly the deportment of various substances and reagents under the flame of the blowpipe, and their treatise on this important branch of chemical analysis was published in 1779. Berzelius, Haussmann, and Wollaston later became interested in this field, and Berzelius, who was notably instrumental in introducing the blowpipe into chemistry, published a treatise on the application of this instrument in 1820. More recently, the art of dry assay, dosimetry, was considerably advanced by the important flame reactions of Bunsen. His treatise, Flammenreaktionen, was published in 1880. After the preparatory investigations of Bergman, Klaproth, Van Quillen, and Proust, it was Berzelius who worked out new methods of quantitative analysis, thereby promoting the systematic development of this branch. He had shown great ingenuity and inspired his pupils, more especially Heinrich Rose and Friedrich Wöhler, with like powers. Rose and Wöhler extended the observations of Berzelius, and made analytical methods generally known by the publication of their treatises. The Handbuch der Analytischen Chemie of the former first appeared in 1829, and passed through 6 German editions and 3 French editions, while the Praktische Übungen in der chemischen Analyse of Wöhler, which was published in 1853, was translated into Russian, French, and English. The chief exponent and great master of analytical chemistry, however, was C. Remigius Fresenius, 1818 to 1897, who for over half a century devoted his life and labors to its extension. He collated and examined all methods formerly in use, and devised many new ones. But his greatest services were the establishment of the Zeitschrift für analytische Chemie in 1862, and the publication of his Anleitung zur qualitativen chemischen Analyse in 1841, and his Anleitung zur quantitativen chemischen Analyse in 1846. These works have been published in numerous editions and translations since. Other chemists who have aided in the discovery of new tests, improved methods of separation and determination, and in the designing of suitable chemical apparatus for analytical operations are Liebig, Strohmeyer, Bunsen, Fremy, Turner, Scherer, Rummelsburg, Gibbs, Blomstrand, Maragnock, and Winkler. Classen's services in electroanalysis have been referred to. Volumetric analysis, that process in which the reagents are employed in solutions of known strength, has been greatly developed during the last 70 years, and volumetric methods are much used in technical analysis, owing to the fact that no weighing is necessary after the standard solutions are once made up, thus saving considerable time. The quantitative analysis of gases was greatly perfected by Bunsen, whose researches in this direction began in 1838. Bunsen published methods of estimating various gases by absorption and combustion, which have required only slight modification since, but the qualitative analysis of gases has only lately been developed in a scientific manner. The work of Winkler in this connection has been important, and he and Hempel have improved the apparatus for gasometry and gas analysis, and have generalized methods. The quantitative analysis of organic compounds has gradually developed from the observation that carbonic acid and water are products of their combustion. Lavoisier indicated the right path here, and his process was improved upon by Gay-Lussac and Thenard, Berzelius, Liebig, and more recently by Densted, Colley, and Hempel. The exact determination of nitrogen only became possible after 1830, when Dumas had devised his method. Other methods of determining nitrogen have been worked out by Will and Wahrentrop, and by Kjeldahl, whose method is extensively used in agricultural chemical analysis for estimating protein. Many methods for determining the halogens, sulfur, phosphorus, and other elements which occur less frequently in organic bodies have been worked out, and these have found extended application in forensic chemistry, hygiene, and agricultural chemistry. The beginnings of phytochemistry, the chemistry of plant life, can be traced back to investigations made at the close of the 18th century. Priestley, Saint-Pierre, de Saussure, and others were familiar with the fact that green plants under the influence of sunlight will remove carbonic acid gas from the atmosphere and decompose it. They were also aware of the fact that ammonia salts are of value in stimulating the growth of plants, Nicolas Leblanc having pointed this out at the end of the 18th century. Although the problems of plant life, the mode and manner of plant nourishment and growth, had engaged the labors of many trained observers for many years, yet even during the first 3 decades of this century, the belief was almost universal that plants, like animals, derived their nourishment directly from organic matter. This assumption found its chief advocates in Germany and France in Albrecht Thayer and Mathieu de Dambossé, respectively. In their opinion, inorganic salts, the importance of which could not be absolutely denied, acted merely as stimulants, and not as if they were essential to the growth of the plant. Indeed, Thayer held that the creation of earths in plants through their vital forces was possible. In this assumption he followed the opinion of Schrader, who so early as the year 1800 imagined that he had proved by actual experiments the generation of the ash constituents of plants by the vital forces. J.G. Wallerius, a Stockholm chemist, had sought to lay a much more rational foundation for agricultural chemistry in 1761 in his Ackerbruchschemiske Grunder, when he made a comparison between the plant constituents and the constituents of the soil in which they grew. It was Justus von Liebig who demonstrated the falsity of the views of Thayer and Dabasil, and who entirely disproved the humus doctrine, as the theory held at that time was called. It was in 1840, after exhaustive investigations on the weathering of rocks, on the formation of soils, and on the effects of rain and the gases which rain holds in solution, that Liebig published his classic work on the application of chemistry to agriculture and physiology. In this, Liebig completely undermined the foundations of the humus theory and enunciated the following foundation principles of modern agricultural chemistry. 1. Inorganic substances form the nutritive material for all plants. 2. Plants live upon carbonic acid, ammonia, nitric acid, water, phosphoric acid, sulfuric acid, silicic acid, lime, magnesia, potash, and iron. Many need common salt. 3. Manure, the dung of animals, acts not through the organic elements directly upon plant life, but indirectly through the products of the decay and fermentative processes. Thus, carbon becomes carbonic acid and nitrogen becomes ammonia or nitric acid. The organic manures, which consist of parts of remains of plants and animals, can be substituted by the inorganic constituents into which they would be resolved in the soil. Practical field trials, carried out by governments and large landowners, proved the correctness of Liebig's deductions from his laboratory experiments, and the many investigators in this line since have come either directly or indirectly from Liebig's school. Liebig's conclusion that one must restore to the soil that which the removal of the crop had withdrawn, if one would prevent its exhaustion, is the basis of successful agricultural practice today. A French chemist, J.B. Boussingault, worked independently along similar lines to Liebig, and the services which he rendered in carrying out researches on the nutrition of plants by new methods were of great importance. Mention may be made here about nitrification in soils and the assimilation of free nitrogen by plants, the most important discoveries in agricultural chemistry of recent years. In 1849, Georges Ville, then director of the Agricultural Experiment Station at Vincennes, proved by actual experiment that certain plants assimilate free atmospheric nitrogen, but his conclusions were strongly disputed, being directly opposed to those of Boussingault and Liebig, and also to subsequent investigations by Lawes, Gilbert, and Pugh in 1857. An important experiment bearing on the point and extending over many years was begun in 1855 by Herr Schultz of Lupitz in Altmark, Germany. He grew lupines on very poor soil, with the addition of non-nitrogenous manures only, and found that, notwithstanding this, the soil became richer in nitrogen year by year. The next step toward the solution of the question was the discovery in 1877 of the now well-known process of nitrification in soils by Schlossing and Muntz. This nitrification being the work of definite microbes, some of which have been isolated, while more recent work has proved that the direct assimilation of atmospheric nitrogen by leguminous plants is brought about by the agency of certain microorganisms, tuberculobacteria, originally present in the soil. Cultures of these specific bacteria are now prepared on a manufacturing scale, under the name of nitrogens, for application to soils naturally deficient in them. It only remains to mention as a factor in the present and future growth of agricultural chemistry the experiment stations and laboratories established now by the governments of every civilized country. In the United States, for example, there are at present 61 agricultural experiment stations, all in charge of efficient specialists, and many intricate problems of national importance have been solved. The large chemical industries, and in fact all branches of chemical technology, have been immensely developed during the 19th and 20th centuries, and the achievements of chemistry in the arts and industries have been stupendous and varied. During the modern chemical period, pure chemistry and applied chemistry have been constantly interactive, and the latter has profited immensely by the extension of the former, while pure chemistry, theoretical, inorganic, organic, and practical chemistry, has in turn been greatly benefited by the opportunities offered by the industries. The advancement of technical chemistry has been especially aided, however, by the development of analytical chemistry, which has allowed of a keen insight into the composition of the various industrial products, thereby leading to the introduction of many technological innovations. Then, too, industrial research has been and is being constantly fostered by chemical manufacturers, and this has led to the accruement of important novelties and improvements. The literature of technical chemistry is very extensive, but the standard treatises of Rudolf von Wagner, Handbuch der chemischen Technologie, Karl Kosmarsch, Geschichte der Technologie seit der Mitte des 18. Jahrhunderts, T.E. Thorpe, A Dictionary of Applied Chemistry, and Ernst von Meyer, A History of Chemistry, translated by McGowan, contains accounts of the development of the important industries. The manufactures of sulfuric acid and soda, which may be looked upon as the basis of all the other chemical industries, and which are naturally followed by those of hydrochloric acid, bleaching powder, chlorate of potash, and other salts of potassium, nitric acid, etc., only attained to their full vigor after the various processes involved had been explained by chemical investigation, and after the most favorable conditions for those processes had been worked out. Important practical improvements were made in the manufacture of sulfuric acid so early as the beginning of the 19th century, e.g., the amount of steam required was regulated and the process was made continuous, the latter by Holker. The first attempt to explain this remarkable chemical process of the formation of sulfuric acid from sulfurous acid, air, water, and nitrous gas was made by Clement and Desormes, who recognized the important part played by the nitric oxide. How essential for the manufacture the careful observations on the chemical behavior of nitrous acid to sulfurous and sulfuric have been is sufficiently evidenced by the introduction of the Gay-Lussac and Glover towers to which they gave rise, and which have made the process into one complete whole. In 1831, Peregrine Phillips discovered the contact process by bringing about the combination of sulfur dioxide and oxygen in presence of platinum, but it was only 40 to 50 years later that Clemens Winkler converted this experiment into a technical manufacture. The contact process, in many modifications, has developed and improved so rapidly that many think it will eventually supplant the old chamber process altogether. Common salt forms the foundation of the soda industry, whose history commences with the beginning of the modern chemical period. Nicolas Leblanc was the first to succeed in converting salt into soda, with sodic sulfate as an intermediate product. Malherbe and de la Metherie, having some time previously attempted to utilize the latter substance in the same way, but without material success. It was in 1791 that Leblanc commenced the actual manufacture of soda, and in the year 1823 Musprat began the erection of his alkali works at Liverpool. His name deserves a foremost place in connection with the development of the soda industry. The formation of soda from the sulfate, by fusing the latter with coal and limestone, was ultimately so far explained by exact chemical experiments as to allow of a tenable theory of this fusion process being advanced. Scientific researches have also given rise to numerous important improvements in the soda manufacture, e.g., to the beautiful process of Hargreaves and Robinson, by which sulfate of soda is prepared directly, without the previous production of sulfuric acid, to the introduction of revolving soda furnaces, and to many processes for utilizing and rendering harmless the unpleasant alkali waste. But the greatest advance of all in this direction is the comparatively recent and exceedingly simple process of chance, by which nearly all the sulfur in alkali waste can be recovered at a very cheap rate. Purely chemical observations have also led to what was, until quite recently, the most important of all the innovations in the soda industry, the conversion of common salt into carbonate of soda without the intermediate formation of sulfate at all, by the ammonia soda process. The manufacture of ammonia soda and of artificial manures has grown so enormously of late years that the demand for salts of ammonia has increased proportionately. But this requirement has, in its turn, been met by introduction of improved apparatus for the working up of gas liquor, and by the successful attempts to extract the nitrogen of fuel in the form of ammonia, at the same time that the heat from the fuel or the residual coke is itself being utilized. Berzelius' experiments upon the bleaching action of chlorine and the chlorides of the alkalis led to the manufacture of the bleached liquor known under the name of eau de Javel. Chloride of lime was first produced by Messrs. Tennant and Company in Glasgow in the year 1779. Weldon's process for the recovery of the manganese dioxide, required in the preparation of chlorine, from the otherwise worthless chlorine waste, has been in practical working since 1867. Deacon's method of producing chlorine directly from hydrochloric acid has never been very widely used. The manufacture of bromine and iodine is based upon the original work of Gay-Lussac and Ballard. Laboratory experiments have also led to the production of iodine from other liquors which were formerly looked upon as valueless, e.g., those from Chile saltpeter and from phosphorite after its treatment with acid. To A. Frank is due the merit of having made bromine available for technical purposes by preparing it from the mother liquor of the Stassfurt waste salts. Nitric acid plays an important part in chemical industries, especially since the development of the manufacture of explosives on a large scale. Potassium nitrate, which has been known and valued for so long, is still an indispensable ingredient of black gunpowder. Since the introduction of the nitrate of soda from the Chile deposits, nitric acid has been prepared from it, instead of from the more expensive nitrate of potash, by the old process of distillation with sulfuric acid, the latest advance here being the distillation of the nitric acid in a vacuum. The explosives, whose preparation now forms a great industry, have all been made available for practical use by chemical investigations. The epoch-making discovery of gun cotton by Schonbein and Bachter, independently, in 1846, must be recalled here. Nitroglycerin had been known as a chemical preparation discovered by Sobrero for 15 years before it began to find extended application in 1862 as the result of Nobel's researches. The match industry owes its enormous development to the increased knowledge of chemical preparations and processes. There is a marked contrast between the chemical tinder of 1807, i.e., matches containing a mixture of chlorate of potash and sulfur, which were ignited by dipping them into sulfuric acid, and the present friction matches. Those prepared with ordinary phosphorus were most probably first introduced in 1833 by Arini of Pesch, and subsequently by Romer of Vienna and Moldenhauer of Darmstadt. They have since undergone many improvements, the most important of these being subsequent to the discovery of amorphous, not poisonous phosphorus, which had been used since the year 1848. Phosphorus has been manufactured on the larger scale for about 50 years. Scheele's process for its preparation was improved upon by Nicholas so far back as 1778, and has been materially modified in recent years. Closely connected also with the soda industry are the manufactures of ultramarine and of glass. The former substance was discovered in 1828 by Gmelin, and at about the same time by Guamet. A little later it was also discovered independently by Gotig of Meissen, who was the first to prepare it on a technical scale. The production of glass reached a high state of development in olden times through pure empiricism, but has greatly benefited by chemical research. The manufacture of glass with sulfate of soda and the improvements in flint and crystal glasses belong to the last century, while progress has also been made in silvering by Liebig and in glass painting through the discovery of new mineral colors. Water glass, which was known to Agricola and Glauber, was made available for technical purposes by Fuchs in 1818 and has since then been used for a great number of different purposes, e.g., for impregnating wood and preparing cements. The attempts to utilize raw vegetable products, particularly wood and straw, for the production of paper were first carried out in the year 1846. In caustic soda, a reagent was found by means of which cellulose could be prepared from these materials, while of late years a solution of calcium sulfite in sulfurous acid has shown itself especially well adapted for this purpose. The above process for the production of sulfite cellulose resulted from the chemical investigations of Tillman. Cross and Bevan's discovery that cellulose can be dissolved by carbon disulfide and soda, and thus be converted into a soluble cellulose xanthate, has enormously extended the uses to which the plastic material can be put. Objects of all kinds, from artificial silk to billiard balls, can now be made of pure cellulose. The beet sugar industry has developed into an enormous manufacture from experiments carried out by chemists on a small scale. Marggraf's discovery, in 1747, that sugar was present in the juice of beet, was not at that time capable of being applied commercially. Achard, a pupil of Marggraf, and others again took up at the end of the 18th century the problem of obtaining sugar from beet on the large scale, and they devised a process which was carried out in factories during the years of the Napoleonic Wars. However, this process was unable to exist, being a very imperfect one and giving but a small yield of sugar, and it is from the year 1825 that the real rise of the beet sugar industry dates, various factors entering into its growth, not the least of which was the practical application of chemical knowledge. Scheibler's strontia process for obtaining the crystallizable sugar from molasses is based upon a knowledge of the various saccharates of strontia. The filtration of the refined juice through bone charcoal was first recommended by Figuier in 1811 and then by de Rosny in 1812, and has since become an essential part of the process. The use of vacuum pans for evaporating the syrup was introduced by Howard in 1813, since which time many improvements have been made in them. Osmosis, which was first applied on the large scale by Damrenfalt in 1863 for extracting the crystallizable sugar from molasses, was developed by researches in physical chemistry. The development of the fermentation industries has been immensely extended by chemical investigation, while at the same time the nature of the processes themselves has been explained. The latest work of E. Buchner and his pupils has resulted in showing that fermentation is brought about by an enzyme, zymase, produced from yeast. Among the more important observations in this branch during recent years are those of Affront upon the favorable effect of a minute quantity of hydrofluoric acid on the fermentation process, and of others upon the advantages gained by ventilation and by the use of pure yeast cultures. A knowledge of the normal composition of wine and beer has led to rational suggestions for the improvement of those liquors. It would be impossible to attempt even a bare enumeration of the more important innovations in this branch, many of which are due to Pasteur, e.g., the pasteurization of beer. In no other section of technical chemistry have there been so many discoveries made by systematic investigation as in that of artificial dyes. The first aniline dye which was produced upon a technical scale was the mauve prepared by W. H. Perkin in 1856, by acting upon aniline with bichromate of potash and sulfuric acid, and it was to him that the introduction of the color industry is due. A. W. Hoffman observed in 1858 the formation of aniline red, magenta, which was shortly afterward manufactured by another method by Verguin of Lyons, and introduced into commerce under the name of fuchsine. This was followed by the discovery of aniline blue, aniline violet, and aniline green, all of which were first prepared by Hofmann himself, while he proved that all of them were derivatives of fuchsine. The discovery of methyl violet by Loth in 1861, and that of aniline black by Lightfoot in 1863, were of great practical importance. In addition to this, new and improved methods for the production of rose-aniline dyes have been discovered and developed, e.g., oxalic acid, formic aldehyde, and carbonyl chloride, are now used for the synthesis of diphenylamine blue, the new magenta, methyl violet, and allied compounds. The valuable dye, alizarine, was formerly prepared entirely from the madder root, but is now obtained from coal tar, this revolution having been brought about by Grob and Liebermann's successful synthesis in 1869 of alizarine from anthracene, a constituent of coal tar. Following alizarine, other derivatives of anthracene were prepared from the year 1880 onward. An immense industry, that of so-called chemical preparations, has gradually been developed on scientific lines from apparently insignificant beginnings, which had their origin in the work of the apothecary. Such preparations belong partly to inorganic and partly to organic chemistry. As instances of this, one may take the great increase in the production of silver salts, bromine, and iodine for photographic and other purposes, and the manufacture of numberless other metallic salts, e.g., thiosulfates, hydrosulfites, borates, and silicates, not to speak of newly introduced compounds like the peroxides of hydrogen and sodium, sodium persulfate and other persalts, and compounds of lithium, rubidium, vanadium, etc. The already imposing list of inorganic preparations is being continually added to. The manufacture of organic preparations is still more extensive. The various alcohols themselves, their ethers and esters, chloroform, chloral, iodoform, aldehyde, etc., are now all essential to the chemical manufactures and to medicine. The processes by which these compounds are manufactured are the result of scientific researches, old and new. From what has been said, it is seen that coal tar is the raw material from which many organic preparations are obtained, the technical importance of which it is difficult to estimate. Formerly a troublesome waste material, it is now of at least equal value to the other products from the distillation of coal. The manufacture of ammonia and salts of ammonia from gas liquor is now a thoroughly rational one, thanks to the careful chemical examination of the latter, and it forms a large and important branch of industry. The manufacture of coal gas was at first developed quite empirically, and it was only in the second half of the 19th century that improvements were introduced, which were based upon the scientific investigation of the relations existing between the composition of the gas and the mode in which the distillation of the coal was conducted, and this also applies to improved methods of purifying the crude gas. The present distillation process was introduced about the year 1880, after it was seen that by raising the temperature of decomposition, the yield of gas from pit coal was nearly doubled. In order to achieve the necessary white heat, gas retorts are now made from the most refractory fire clay instead of iron, and they are heated by regenerator gas. About 15 years ago, acetylene began to come into prominence as an important illuminant. Indeed, enthusiasts on the subject prophesied that the brilliant light which it gave would prove to be the light of the future. Produced from calcium carbide, a product of electrochemistry, it looked for a time as if acetylene were destined to become a formidable competitor of the electric light. The first impulse toward the use of furnace gas as a heating agent was given by the experiments of Faber de Faur and of Bunsen, experiments made with the object of utilizing the gases issuing from the mouth of iron blast furnaces, which are rich in carbon monoxide. These, as well as the gases from coking ovens, were for long allowed to escape, and still are to some extent, but for the most part they now constitute important sources of heat. Lowe introduced water gas into technical use in 1875, preparing it by passing steam over red-hot coal. It is now much used for heating and illuminating purposes, and will undoubtedly become even more employed in time. The above resume of the development of industrial chemistry during the modern period will indicate how it has been elevated by a continuous infusion of scientific spirit, and manufacturing, once a matter of empirical judgment and individual skill, is more and more becoming a system of scientific processes. Quantitative measurements are replacing guesswork, and thus waste is diminished and economy of production ensured. In the United States, several decades ago, few industrial establishments furnished regular employment to chemists. But now, American manufacturers are becoming more and more appreciative of scientific research, and the results so far obtained have resulted in far-reaching improvements in the production of a metal from its ores, or of indigo from coal tar. It is chemistry that points the way, and the more complex the problem, the greater the dependence. In devising new processes and in the discovery of new and useful products, chemistry is again the pathfinder. The community is apt to overlook the extent and diversity of the services rendered by the chemists, because of the quiet and unobtrusive way in which the work is carried out. The measure of a country's appreciation of the value of chemistry in its material development and the extent to which it utilizes this science in its industries generally measure quite accurately to the industrial progress and prosperity of that country. In no other country in the world has the value of chemistry to industry been so thoroughly understood and appreciated as in Germany, and in no other country of similar size and natural endowment have such remarkable advances in industrial development been recorded. And this, too, with steadily increasing economy in the utilization of the natural resources. Ex-President Roosevelt has well said, quote, "The life of the nation depends absolutely on the material resources which have already made the nation great," unquote. And M.T. Bogart recently has eloquently indicated how the chemist can and will be of service in that great problem, the conservation of natural resources. This work is not entirely that of the engineer, and, with the awakening of the producer and manufacturer to the value of science and industry, the outcome of the conservation movement can only be a successful one through the assistance of the chemist. End of section 21. Recording by Warren Kati, Gurnee, Illinois. End of The Science, History of the Universe, Volume 4, Chemistry, edited by Francis Rolt-Wheeler.